would probably increase the scale of what we can do, which would be great. So with that said, I'll introduce our keynote speaker. We have Alessandro Fanfarillo. He was an employee here at NCAR for a few years. I don't remember the exact number of years, but he could tell you. I believe it was 2020-ish when he left NCAR to go to AMD and basically work on exascale GPU computing and all that sort of exciting stuff, and challenging things like porting scientific codes in a performant way to run on massive systems with lots of GPUs. So he's in his time here at NCAR and obviously at AMD, he's certainly done his work with an eye towards improving scientific software and making it run more performantly and letting us handle bigger problems. So yeah, with that said, I'll let Alessandro take over. He's virtual, so we'll get him up on the big screen there. And Alessandro, I'll let you take it away. Thanks.
Thank you, Brian. Thank you for the introduction. I'm gonna share my screen. Make it big. Can you guys see the full screen slides?
Yes, we can. Thank you.
Perfect. So you can also hear me and possibly see me. Okay, thank you again, Brian. I worked at NCAR for 4 years, so it was a pretty long time. And yes, as Brian said, around 2020, I left and joined AMD to basically be part of this Frontier Center of Excellence, which is basically a set of people. It's Center of Excellence is a DOE terminology that encompasses a group of people coming from different organizations, all focused on making sure that the machine that we're trying to build is going to work as expected, and the performance are what they meet the target, basically. So with that being said, today we are going to talk about porting legacy codes to the Exascale era. Well, first news, the Exascale era is already here. If you haven't seen any recent top 500, we successfully built Frontier, which is the supercomputer on the left. It's the very first exascale supercomputer in human history. It reached 1.1 exaflops in double precision, and it opened to all the users a few weeks ago at Oak Ridge National Lab, and it's going great. So we are very proud of this result. And I'm going to focus my presentation mostly on this because that's where my work basically focused over the last 3 years. On the right, we have our next challenge, which will be even more challenging than Frontier, which is El Capitan, which will be the second exascale supercomputer and hopefully the most powerful again when it comes out. I cannot say too much about this because it's still ongoing, but that's our next step for the exascale era. All right, I want to talk a little bit about what Frontier is about, even if you may not use it directly. I just want to give you an idea of what Frontier is about in terms of hardware, the challenges, and then we're going to talk about how to make sure that your codes can run on Frontier or any other exascale system smoothly and possibly, without too much effort on your side in terms of programming and software engineering. All right, as I said, Frontier is deployed at Oak Ridge National Lab. It's 9,408 nodes. It's a huge machine, potentially can reach almost 1.7 exaflops. Of course, there are power limiters and scalability limiters, but we achieved 1.1, which is the first time. Please note that even though this 21 megawatts of power, it's scary to me, to be honest, but it's the most efficient supercomputer in the world in terms of energy per flop per watt. So it's pretty good number, despite being very big. How is it composed, which is what kind of it's more interesting for you. It has, each node of Frontier has one optimized AMD EPYC Zen 3 CPU, but it's kind of optimized because it has special channels, memory channel that connect the CPU to the various GPUs in a very fast way. So it's a Zen 3 like Milan, but it's a little bit better and specifically designed for this particular GPUs. What are those GPUs? Are the MI250X. It's a very new device, and the most innovative part, let's say, is that it has this infinity fabric links on the sides, the one that you see here, down here, on top and below this purple. I don't know if you can see my cursor, but basically this links here connect this chip to either the processor or to another chip like this to make kind of a two, it can be seen as the two devices, but actually it's one that gets cooled in the same socket and with the same system, let's say. So it's a very new device and very unusual from what we have seen in the past. Each node has 4 MI250X and a total of 8 of these little devices. So if you want to use one node on Frontier, you need to use at least 8 MPI processes, or your single MPI process has to use 8 different devices, because these little purple things look like a device to the user, but actually the card is 2 of this. So it's a little tricky. What is the most interesting part for you and for the future of, if you want to run your codes on an Exascale machine like this, is the coherent connectivity. So there is this infinity fabric, which is this these connectors that I showed you here that are tightly integrated with the CPU and with other GPUs in the system, and it's a whole unified memory space. And that's the real deal that you should care about as software engineers. All right, I use Fortran for this example. We can use C++ as well. It's not a big deal. Of course, there are changes that I wanted to keep kind of a syntax that it's not exactly Fortran here, for example, but I'll tell you more in a moment just to clarify a little bit what it is. All right, what is this coherent programming model? It's basically making the transition from CPU to GPU very, very easy. You have your CPU code here, your weather, climate, hydro, whatever you like. And you have your Fortran code, you allocate your memory, you do your do loop, you call a CPU function, let's say, that it's very, very expensive in terms of computing. And you read the data out and you write it on disk or whatever you do. The GPU code in the past, or at least for the most portable way of writing GPU code, would be to call something that basically allocates the memory on the device. And this heap malloc, it's something that we use. Heap, it's something that I can talk more about later, but it's not really the point here. It's like the equivalent to CUDA, that it's an NVIDIA proprietary programming model, programming environment, let's say. We have heap. It's pretty much one-to-one almost. But the point here is that if you want to port a CPU code to a GPU code without this programming model, with coherent programming model, you would have to deal with this type CPT, C pointer, to keep track of C pointers that get allocated by function calls kept in C++, let's say, on another part of your code. Do whatever you were doing on the CPU, which is the host. In fact, we have in _h as a host. Then manually copy the memory to the device, call a GPU function with some heap syntax that it's not really here, but this is just to give you an idea that you need to call this from a C++ layer, and you can do this with ISO-C binding in Fortran. Then you need to synchronize whatever was working on the GPU with the device, with the host, and then you want to copy the memory back to the host, and then you can write it on disk if you want. So this is all good. I don't mind doing it, but it's incredibly tedious. It's very error prone, and it makes the code very messy, which we all know that our codes are already messy enough. We don't need extra code to make it even more hard to read. So this is what you can do as for today on Frontier or other AMD devices. You just write your basically your code, like you were doing on the CPU, you allocate it, as if it was CPU memory. You initialize it with a loop. You call your GPU function in heap, let's say. You synchronize, and you're done. You don't have to do all this allocating memory on the GPU, moving memory, moving it back, and so on. The system takes care of everything. So this is a big deal, because now all you need to do, which is still challenging, but it's less tedious and time consuming, is to just write your GPU function with a language that our GPUs can understand, and you're good. You don't need to do anything else. This is for the most advanced users that really want the performance of the GPU to exploit it as much as they can. But it's kind of hard to, well, let me tell you a little more about this XGMI, and then I'll tell you the alternative to that, which is another way, and it's probably more suitable for when you need to port big codes, when you really cannot afford to write from scratch GPU code for many parts of your code. So let's talk for a moment about the performance of this approach. So here I brought back the coherent code, which was the rightmost in the previous slide. And this is better than before, let's say, from whatever you have seen, thanks to those Infinity Fabric links that are directly connected to the CPU. So you have the CPU here, this particularly efficient, optimized Zen 3 processor, connected to this MI250X with this basically XGMI link. And you can reach up to 56 gigabytes per second, which is pretty fast for this particular technology. All you need to do is, as I said, you don't need to do GPU allocation anymore. You don't need to do any explicit memory management. You just need to synchronize to make sure that the host can see what the GPU has done at the end. There is an alternative that I was talking about, and it's OpenMP target offload. So instead of writing a brand new GPU function that replaces your compute-heavy CPU function for your scientific code, you can use this particular directives that the compiler, if the compiler supports this sort of technology, can actually make this transition for you from CPU to GPU and offload this code, this basically loop. Usually you focus this directives on top of big loops, but you can do it with other things too, directly to the GPU using this unified share memory keyword. So if you're familiar with OpenMP, you know what I'm talking about. If you're not, look up for some OpenMP directives, how they work, and then what the magic word is target offload, which basically allows you to move a certain loop or compute-intensive part of your code to the GPU seamlessly. The good part is that the runtime in this case knows it can omit copies, explicit copies, and map clauses. And so it can basically do everything under the hood for you. So all you need to do to run on the GPU is to add a few directives that have to be consistent with what you want to do, of course, but that's it. You don't even need to write the GPU code in heap or, which is the equivalent of CUDA. Of course, this has the final result in terms of performance might not be as good as the one you will get with a heap code, but it's good enough to run on a GPU. And most of the codes used at Oak Ridge use this approach in particular for Fortran. So what are the challenges? I'm going to go a little bit faster, but this is a very important slide. What are the challenges of porting the CPU, a code from CPU to GPU? First of all, you need to understand if the code exposes enough parallelism to justify the GPUs, mostly because GPUs are very different devices from the CPUs. So if you see a part of your code that can be very much parallelized, that's a good candidate for porting the part of your code to the GPU. You don't need to port everything, but that you can start from the one that it's more compute intensive and it's parallelizable. How do you know that? What parts of the code you should be porting? Profiling. You need to see how much data gets transferred potentially on the CPU and GPU, because even though it's very fast on our hardware now, it's still slower than having it on the GPU all the time, because GPU memory is way faster than the little link between the CPU and the GPU. What technology should you use? This is probably the most important choice that you have to make when you want to port a legacy application to the GPU. As I said, the first choice, personally for me, it's programming with HIP, which is C++ code, and invoke that particular routine from Fortran. So you write C++ code, you have this hooks to the Fortran CPU code, and you have the full control of the whole situation. You have overall the best performance. If the code is not performing, it's your fault, which is great because you can fix yourself easier than fixing a compiler usually, and it depends on you most of the time. The problem is that it's low level, can be difficult to maintain, and it has a higher cost of porting from legacy code because you have to write new code again. And when you write code, you introduce new bugs and you have to debug it, and it gets complicated. Another good option that we currently have, and most people use it successfully, is, as I said, OpenMP offload capability. The porting, it's way smoother and easier to maintain in case you need to change the code after the porting. You just need to add the directives and you can run on the GPU. The problem is that it relies on the compiler support for OpenMP offload and also for the quality of the implementation. So if the compiler you're using or you have available, it's not great for certain things that you're using, you are stuck, and that can be a problem. So you need constantly talk to the vendor that provides the compiler that they need to improve certain things, and there is a delay there to get the performance you want, mostly because the compiler is the limiter and there is nothing you can do about it. These are other two very valid opportunities, but this one is mostly focused on C++ code, so it's totally not applicable to Fortran at the moment. It's portability layers. Basically, these are frameworks, codes that have the target of running on different hardware without changing the code with by providing reasonable performance portability. The problem with this approach, even though it sounds very enticing, is that you need to rewrite the code using the portability layer, which usually is used in the C++ community. What I really encourage you to try, if you can, is this fourth option, which is rely on libraries and packages. If your code uses, let's say, lots of matrix multiplication, sparse matrix multiplication, solvers, stuff that it's basically well understood in the community, don't try to rewrite your own. Try to use a library or something that allows you to run also on the GPU, because those implementations are very high quality. They will just expose an API, a function that you will call, and the porting is seamless and the performance is awesome. So even if you are doing, for example, Python codes, you can use Numba, you can use JAX, you can use various libraries that allow your Python code, Fortran code, C++ code to run fast on the GPUs. The problem is that if the code doesn't rely on general routines or patterns, you cannot rely on this. Okay, what are the opportunities of running to do this porting? And this is my last slide, basically, so I should be still on time. Well, of course, when you successfully port the code from CPU to GPU, you have higher performance, faster time to completion. You reduce the number of compute nodes required for your run, so you save more compute hours. And if you're really interested in doing some more cool stuff, you can do an ensemble run by tweaking a little bit, the initial condition and run and all, and do some statistics on your simulations. Another very important one is running on the GPU improves the energy efficiency. So you get more bang for the buck, more computing power in fewer watts, because the GPUs are very efficient and energy efficient in doing parallel, running parallel code with fewer watts than CPUs just by design. Third one, which is usually kind of understated in people that try to convince scientists to port the code to GPUs, is that, funny enough, refactoring CPU code to be GPU friendly could also improve the performance on the CPU code when you're not running on the GPU. Let me tell you why. Your code, you write your code maybe 10 years ago, it works on the CPU fine, but it's messy. Messy, like your accesses are not really cache friendly. You may have, you're not taking advantage of vectorization because 10 years ago wasn't a thing as much as it is today, and loops are a little complicated. So you want to port it on the GPU, you start refactoring your code because now you have to deal with certain exposing parallelism to take advantage of the GPU, and you rewrite also your CPU code because you think it's better. And when you run that code on the CPU again, it goes faster because it's written better and more, it exposes more parallelism that the compiler on the CPU can actually take advantage of. So it's a win-win. You could also find a way to switch from ad hoc algorithms for, let's say, your solver to library calls that actually improve the performance everywhere where you run it, on the CPU, on the GPU, on whatever technology will come tomorrow. And the basically the strong tendency to performance portability, it basically relies on this use of libraries and portability frameworks. So if you really want portability in the end, and you're doing this work of writing your code from CPU to GPU, try to use as much as possible the portability layer, because that will pay itself off over the years, because it will allow you to run your application on pretty much anywhere you want. Okay, the conclusions. This is a very, very important statement. Exascale computing is a paradigm shifting capability. It's not in programming models. So if you want to run on an exascale machine, you don't need to do another, you need to use another programming model. It's not that different. The traditional techniques of scientific computing that have been seen over the last 15 years, like CUDA, HIP, OpenMP, MPI, are still very effective. Our code on the GPU, on our GPUs on Oak Ridge, run with MPI plus X. Basically, you have the MPI code plus OpenMP or HIP. And it's the most viable internal programming model. And it's a success story in particular because we use GPU-aware MPI plus X. So the MPI implementation on Frontier is aware of our GPUs, and the transfer go from GPU to GPU without going to the CPU when we go internode communication. Performance portability is not easy. So the right technology that you want to use to port your code should be chosen based on the software engineer capability, because software engineer has to be aware of what's out there and how to use it as best, the targeted machine, and the application lifespan. Because if your application, you want your application to, have a very long lifespan, you need to choose a technology that is stable. You cannot disappear tomorrow. Fortran is here to stay. It's not going away. So if you have a Fortran code, stick with it. It's not going anywhere. However, C++ coding skills may require for achieving high performance on GPUs, because you have to write some heap code. So be aware that C++, it's strong in the HPC community, in particular for Exascale. And the compiler support for OpenMP offloading in Fortran is available, but performance may vary. So just be aware of that. Finally, several packages and libraries in languages other than C and C++ and Fortran now support AMD GPUs. So if you do machine learning, Python, data analysis, pre-processing, you can still use the GPUs with certain Python libraries. So and makes the task pretty much seamless. So it's an exciting time, and I hope I have just to show you this. And I hope you'll have the chance to run on our hardware and hopefully to get some good results. And I'll take any questions. Thank you.
All right, thanks, Alessandro. Yeah, so we definitely have some time for some questions. I didn't say this before the talk, but for anybody who's virtual, if you check the chat on Zoom, there's a Slido link. So feel free to type in questions in there. And then for folks who are in the room, I think we have a mic up there if you want to walk up to that, or I can also bring you a mic if you raise your hand. If you prefer that, that's fine too. So I guess I'll ask a question first, Alessandro. People are collecting their thoughts. I think one thing that has been a bit of a challenge, or at least something to pay attention to here at NCAR when working with CUDA and OpenACC and OpenMP is whether you're kind of directly, moving data and directly managing the memory, or whether you're kind of doing automated memory management. Can you speak at all to sort of considerations that you all have seen at AMD in terms of memory management and, you know, maybe best practices for the codes that you've worked with?
Sure. Definitely memory management is the killer, in particular if you start porting the applications bit by bit. So you have your REST application, it's all Fortran on the CPU, and then you have this big function on the GPU, and you have to move data back and forth every time in a loop. That it's gonna kill the performance, because moving data it's basically the killer. The suggestion what we do usually is identify what function we want to port, and in particular, one of the criteria that we use is how many times do we need to move data in and out to this function. We try to identify the one that doesn't need to move too much data all the time, and possibly that has a very, very high reuse of memory that doesn't need to go out. So let's say you have a function that just takes an array as input and spits out an array as output, but inside it uses a lot of memory. What we do is there's a lot of memory that the function uses, gets allocated once at the beginning, stays in GPU memory. The function can use it as many times as it wants, and we just move in and out the arrays that we need to. Another thing that I mentioned at the end is if you need to move data in and out because you need to pass that data with MPI, try to use a GPU-aware MPI, because it will still, depending on your hardware, of course, on Frontier it doesn't need to go through the CPU, but because it goes GPU to GPU directly, but still it will go faster if you use an MPI implementation than instead of doing it manually, moving to the host, keeping the memory on the host allocated, and which wastes CPU host memory again, and then pass it to another MPI buffer that again it's another transfer. So the suggestion is try to identify the function that actually how to minimize that, how to minimize the data transfer, including with the use of some MPI aware, GPU aware MPI, that even though you're still transferring data between the CPU and the GPU, it's more efficient. And I can give you more detail. Why is that more efficient? But I don't know if this answered the question completely. It's at a certain point you have to bite the bullet. Unfortunately, moving data in and out is the problem. So ideally, you want to port the whole code on the GPU, so you don't have to transfer anything on the CPU. But when you are in the process, you will see probably a slowdown by using the GPU if you start moving too much data in and out. That's still the problem. This will not be the problem, I have to say, for example, on El Capitan. I can say this because it's public, but AMD is working on the MI300A, which is an APU. And an APU is basically a single device, CPU and GPU all at once. So the CPU and the GPU have exactly the same memory in hardware. It's not a link between two devices, it's one thing. So if you, like, for example, you start porting your application now and you're still doing lots of transfer in and out of the CPU and the GPU, in 5 years, maybe you will have access to an APU and that cost will completely disappear because you will have CPU and GPU memory that will be basically the same in hardware. So that's kind of a good investment to do now, to keep in mind. But again, it's transient. It's not here to stay, at least for our technology.
Yeah, thank you. I think we have a question in the room and then a question online as well.
Hello, can you hear me?
Yes.
Hi, Alessandro. This is Wei Ming. It's nice to see you. And also,
hi, Wei Ming.
Yeah, excited to see all the work you've been doing at AMD. So I have it's interesting you mentioned towards the end of the talk, saying that porting from CPU to GPU actually improves your design and performance for your code. So I was wondering, what's the implication for somebody like me, a majority of like Python developer? Because most of the time, when I switch my code from CPU to GPU, I just switch a directive and just say, okay, use GPU equals to true, and that's what I do. So what do you what's the implication in this case? Are you suggesting that when I start off writing my code, let's say designing code for pre-processing and post-processing, I should be thinking about doing it on the GPU from the get-go? Thank you.
It's a good question. It depends on how much data you are processing. If you just need to do, you know, very little mathematical operation on that array, let's say, probably not worth it. You can do it very fast on the CPU. What it's really worth doing on the GPU in Python in particular is heavy mathematical operations. You know, it's obvious, but that, you know, machine learning for sure, it's one of them. It's definitely great, but also you should keep in mind that if your algorithm in the background, you need to know a little bit how your algorithm is working. For example, if you're doing something that happened to me recently, Markov chain Monte Carlo, if you want to do some Bayesian analysis when you have a probability distribution and you want to do sampling of a posterior for your statistical problem, and you need to use a Markov chain Monte Carlo, which is very much serial. It's, you know, you have a bunch of chain that run in parallel, but each chain is serial. Running on the GPU, it's not the best. You may have the same performance as you have on the CPU, even though your GPU is very, very powerful. Why? Because the algorithm, it's intrinsically serial. If you are doing, for example, again, a statistical example, a Gaussian process, when you have this sort of non-parametric Bayesian model that needs to do a bunch of Cholesky factorization in the background, if you have a lot of data and it has to, it's a complexity of n cube, where n is the array, GPUs can be good, because at that point you have lots of compute that needs to be done on the GPU and it can give you some benefits. So be mindful of what algorithm you're using. And if it's very much you don't need to understand all the details, but just try to get a sense if it's very much a serial algorithm or if it can be parallelized very well. Google it, I would say, at a certain point, is how well this algorithm goes on the GPU. And that will give you an answer to if you want to start directly on the GPU, or if you want to evaluate it with your problem size, because the other problem is problem size matters. If you have a very small problem size, there is no point in using the GPU. If it starts getting bigger and bigger, at a certain point you have a dominance from the the GPU computing power. But deciding where this point is, it's very much an empirical approach.
Great, thanks, Alessandro. Yeah, I'll get to a question we have online in just one second, but also just a quick note for the next speaker, if you could join us in the back of the room, we'll kind of get things set up. Yeah, so we have a question online. So let's see, sorry, I need to manage my tabs here. Yeah, so I think the first one that was up, it's from Sean Bruno. There's been some interest in Rust for computing due to its focus on concurrency. Has AMD been investigating support for Rust bindings for MPI for GPUs?
Not that I'm aware of, and at least we have never received a request for Rust yet. It's a pretty good point. It's getting lots of traction, but no, the scientific community, it's very much C, C++, Fortran, C, C++, Fortran, that's all it is. We have Python, of course. We don't have R at all. And I was a little surprised, but at Oak Ridge at least, and also Livermore, it's all C++ and Fortran.
And then I think we have time for one quick question here in the room.
Hi, with so many different types of GPUs now, like AMD with Frontier and Argonne's getting Intel GPUs with Aurora, and then NVIDIA CUDA is already there. So going forward, like 5 years down the line, I think it's already a nightmare, like porting or seeing that PyTorch works on one, doesn't work on the other, or there are several versions or so on. So is the community coming to a consensus? And as a programmer, what do you think one should invest time on? Like, is it a good time to start programming on CUDA? Because now there are other competitors and there's OpenMP, what standard? So just would like to know your thoughts on this, and how's the community coming along? Thanks.
Yeah, absolutely. So you mentioned PyTorch. I guess you are interested in mostly machine learning, or you're talking more about the whole thing, HPC or machine learning, and machine learning together?
both. Though machine
Okay.
learning is something that I work on, but yeah, I work on something else too that is general around, yeah, just using GPUs, not for ML, but other stuff also.
Okay. So for ML, good news. The community actually has an agreement that there are layered like JAX, Namba, and things like that, XLA, that make this running on across devices for TensorFlow and PyTorch seamless. So I personally run on NVIDIA GPUs, AMD GPUs with PyTorch and TensorFlow seamlessly. So machine learning is in a great shape for running on different hardware without changing the code, in my opinion. And the performance is splendid. It's very, very, very good. In efficiency, it's very low. There is lots and lots of traction because, all the chat GPT and other recent improvements in machine learning and AI. So if you do machine learning mostly on GPU, you should not be worried about portability because that will stick around for at least the next 5 years for sure, and will go up and up and up and up and up and up. So it can only improve from here. HPC. We tried to create this heap, which is basically a portability layer, which allows codes for low-level codes, I mean, like written in C++ with explicit parallelism, CUDA-like, to run on both AMD and NVIDIA hardware by using the same code. So if you write your heap code, you can run basically on both vendors seamlessly. There are other techniques. There is, talks about how to do depification from a CUDA code. There are tools. It's not difficult. There are some slight differences, but it's pretty straightforward. Even better than that, what we really advocate is relying on an open standard for directive-based offloading, which is OpenMP offload. OpenMP offload will definitely stick around. It's not going anywhere. It's not like I'm talking about NVIDIA now, OpenACC, which is proprietary. So when you write your code in OpenACC, you cannot run it on our hardware unless you have some kind of magic that does the translation under the hood from the compiler, which it is available for certain system integrators like HP. But for maximum portability, for maximizing your effort now, and try to decide if you really want to the best performance, but you have to maintain basically a C++ code and a Fortran code or whatever you use for the host, and then you use heap, or you use OpenMP offload, but be mindful of the support of the compiler that you have available now. Compiler support improves over time, but it's glacier pace, like very, very slow if there is no traction from a big customer like DOE. So try to evaluate, to think, that's what I was saying in the slide. It's try to understand what's the lifespan of your app, try to understand what machine you're targeting. At Anchor as well, if you have, you want to run on the ratio, try to see what compiler will be available for the GPU OpenMP offload and see if it's a viable option. If it's not, you need to step back and try to write your code with something that it's a little more accepted by the system, and keep your mind open in terms of design with okay, if tomorrow we have an AMD machine with MI300A instead of NVIDIA, this will not be a problem. So maybe you design your code accordingly and try to make it, kind of be, have some foresight, basically. That's kind of my take over this. So machine learning, don't worry about it. It's can only get better from here. HPC, you need to think about where you want to run in 5 years from now, in the next 5 years, if you are looking at the 5 years horizon.
All right, well, thanks, Alessandro. I know there are some follow-up questions and some other questions that we have both online and in the room, but we do need to keep to the schedule. So we just give, we have a short comment of Kokos, but yeah, unfortunately not time to comment on that, Alessandro, but thanks for your time, and let's give Alessandro another thank you.
Thank you, everyone. Thanks, Brian. Take care.
All right, so our next speaker before the break will be Christina Holt from Series NOAA, and she's going to give us a talk on a unification strategy for UFS workflows. So yeah, whenever you're ready, Christina, take it away.
Awesome, thank you. So I do want to quickly acknowledge my collaborators. I am from GSL over across town, and my collaborators here are scattered all over the country and work for the Earth Prediction Innovation Center. They come to us from Raytheon and Element 84 there, but this is not just us. This is a very broad community effort to unify the UFS workflows. Because we're NOAA and UFS and EPIC, there's going to be an alphabet soup that I'll apologize beforehand for here. But I do hope to get into some of the more detailed software aspects of this that I can't typically with more scientific crowds. All right, so let's start off with the what is UFS, just in case you may not have heard it recently or ever. The Unified Forecast System is a community-based, coupled, comprehensive Earth modeling system. So it's meant to span local to global domains and predictive timescales from sub-hourly analysis to seasonal predictions. It's comprised of several applications that share agreed upon numerical weather forecast system elements. There's a whole host of those types of elements, but like think pre-processing for data, forecasts for the atmosphere or ocean, and post-processing, among many others. Data simulation is also thrown in there. And then the UFS also encompasses the infrastructure such as model coupling and workflow software. This was pulled directly from the UFS website. And I will say that a lot of the pieces of this have been achieved and unified over the past many years, but we're still kind of lacking there in the workflow software. What I do want to kind of put together in my own thoughts is essentially we're all running the same components, just configured in different ways. So let's build a system to support that. A bit of history on this project. It started not as the first project of this kind, but maybe the fifth or sixth to unify across multiple numerical weather prediction systems. But this one started with a UFS research to operations project that was working on defining the requirements for all of the UFS workflows. It started with a workshop back in 2020, one of the first that we had in the pandemic remotely. What came out of that was really just the idea that we had too many workflow solutions, and we really do have a desire to consolidate those. We formed a small working group. At that point, we met pretty regularly to create workflow diagrams, see where there are commonalities among the three major apps that we have been targeting so far. That's medium range weather, short range weather, and the hurricane analysis and forecast system. So these are the three main ones, but we have several other systems out there that we would like to also target. We have multiple one-on-one meetings with a whole variety of different groups, small gatherings, including developers, scientists, the steering committee for UFS, leadership of these programs, and many others as we were refining those requirements to deliver at the second workshop in 2021, where the community really was supporting us pushing forward with the development of this. We have a well-defined problem. Now let's do something about it. So we were able to join that working group with a fully supported EPIC team. EPIC, again, is the Earth Prediction Innovation Center. And now we have the Unified Workflow team. It's a mixed institution team and the first of its kind on that program, working under the scaled agile framework project management approach. We started back in 2021 in the late fall by adding work to our feature backlog, or just the list of things that we needed to get done. We built a team of engineers and started looking for additional funding opportunities to get the project off the ground. Here, EPIC was already providing us a Scrum Master for our Agile team and a software engineer. NOAA EMC, the Environmental Modeling Center, and then GSL, my lab, Global Systems Lab, provide software engineers and contributions in kind at that point. Today, we've started working to fill out the Agile team a little bit more. We still have Me leading that team as the product owner, my co-author Frederick is our Scrum Master, pushing us toward the right direction. And then we have a variety of software engineers and developers from Epic or NOAA GSL, and funded through a couple of different initiatives at this point. The Joint Technology Transfer Initiative and the Software Engineering for Novel Architectures project that we're a part of through the NOAA GSL collaboration. That one's pretty cool in that not only are we looking at workflows to run across multiple systems carrying us into Exascale, but we're also looking at other things like running on CPUs and GPUs for numerical weather prediction system. So this seemed like a good fit here as well. And then we have a bunch of different institutions represented by our stakeholders. Here, we're still involved with the Environmental Modeling Center, my lab, the PSL down the hall. Of course, we have RAL and DTC from NCAR, and then JCSDA for other inputs on the data assimilation front. The team came together around a common vision that came out of those requirements and workshops. We're looking to build modular, portable, robust frameworks for running the UFS. We need to support both research and operations at NOAA. And we want to take a services-based approach to ensure that we can have extensibility and usability of each of these components or services by all of the UFS applications that are trying to use those. We also want to develop a user interface that isn't a nightmare and can be pretty easily learned quickly. The goals for our team to obtain that vision, of course, always obtain more funding, and we want it to come from a variety of locations so that we can get that buy-in from NOAA leadership to say a lot of folks are supporting this effort. They see the value in it, and now let's go for it. Another way that we can ensure buy-in from that leadership is to regularly release our tools so that we can start to have an iterative design process, show the value as early as possible. And of course, then for all of our practices or all of our tool sets, we are applying software best practices so that we can make sure that we really do have a well-tested, easy to use toolbox to support this effort. We have a strategy here, and I'll talk a little bit more about each of these pieces as I go along, but in the short term, we want to develop a set of standalone tools. These are going to target those high maintenance problems that people will really start to see the value of a nice tool that can solve some of their problems so that we can start to get that iterative design approach in there. And then we'll start to get them incorporated into the existing applications. In the medium term, though, we want to start moving away from standalone tools that are just incorporated here and there and move toward an entire framework that has been designed around a service-oriented architecture to achieve a plug-and-play type feel that a lot of our scientists have suggested might be the way to go. We do realize that that architecture is going to require many interfaces to the existing component drivers and existing workflow managers that we have out there. Some of our favorites in our community include EasyFlow, Silk, or Rakoto to manage numerical weather prediction systems. And then long term, we are going to be looking at implementing the Strangler pattern after we get that service-oriented architecture design implemented. So we apply a facade there that can switch between the old way of doing things and the new way with the new services that we're introducing. This multi-year approach really allows us to start unifying gradually, iterate often in that time frame, and then add value as soon as we possibly can. So just a quick look at some of the standalone tools that I'm talking about here. What are the bottlenecks in current systems? Everybody does it differently in each of the different apps, even extending to their own way of doing it in their one-off workflows. Configuration management is one of the big ones. We started with the UFS weather model that's based around FE3. Currently, that model requires about 10 different types of parameter files to be staged in the working directory before you call your MPI run job. It's a lot. It's a huge learning curve. Each of them has its own unique way of defining syntax and what's expected, and that sometimes the same information is expected over multiple different files here. These tools that we're releasing early on are going to allow us to essentially fit those variety of files with a YAML interface. So we're moving toward a standardized approach to configuration here, at least at the user level, so that we can improve organization of how we're providing information. We can talk about readability here all in one file, and understanding what's interacting with what other sections of your configuration. I think that we'll also see some benefits at the app level for this going into the model and in the app. We can start to decouple the weather model version from the workflow. That means there would be increased compatibility between those two where there's tight coupling currently. And the tight coupling then comes from how those files are managed. Often it's a copy of a snapshot of a version of the weather model's input file that goes into the app. And then every time you want to update that version, you need a new copy of that file. Instead, we can just pull it straight from the regression test, for example. That's a fully tested file that we can make some modifications to. The Python-based approach opens new doors for configuration validation. Many of these entire apps are scripted in Bash and don't give us many opportunities to call on other outside packages to do this work for us. And additionally, a self-serving thing here for our team is that these really will become a foundation for the configuration subsystem of the whole unified workflow. So we're not just providing a standalone tool, but the capabilities of expanding to the next phase of the implementation. Other little types of jobs here that we'll definitely need. Everybody's running on a system with a batch system. So the workflow managers that I mentioned earlier, some of them provide this the SBatch card for you, or the PBS card. Others do not. So we need to make sure that that's a unified task. It's pretty simple, but it can help us to interact with exactly what resources a given job needs and tell the computer about that. File mover is another one that really can start to bog us down if we're talking about moving from one place to another where data streams may not exist on disk, where we may want to pull from AWS to a local platform or move between various HPC platforms that you may have access to. So giving the users a standard interface for how to do this with some information about protocol and where these data sets live could really help us move forward with some of the community support that Epic is trying for here. So far, I've talked about some of the services or standalone tools that we are aiming at first to help relieve those aches and pains that some of us feel, but we do want to move eventually toward a unified framework. And we think that a service-oriented architecture is going to be the way to go as far as the pattern goes for the architecture. A service is any software component that provides some functional capability. Those services can communicate with each other across platforms and languages, and they can be reused in different systems. Multiple services then can be combined together to do more complex tasks. So this is just a very basic, what is a service-oriented architecture? What is a service kind of definition? But I do want to make sure that I'm very clear that we're not talking about software as a service, which is something that people kind of click on in their head as we're talking about services. This is distinctly different from the cloud computing model, where we're providing some service over the internet for users to access from their web browser or similar. In that model, users don't need to install or manage their software locally. We're not trying to get away from that. We know that our user base, our developers all need to install all of their components locally and work on those in a development environment. So just to be clear, SaaS is not where we're going here. With unification, the service-oriented architecture, though, is that architectural approach that we would like to take. It encompasses the design principles patterns and practices for building exactly what it is we're looking for here with unification on the modular, interoperable, and scalable software system. Just one more quick visit to what a service should be, just a chunk of code that is independent. Our current run scripts, for example, are all tightly coupled in ways that frighten me in some instances. So changes to one service wouldn't impact other changes versus our current system where you may have to change 10, 15, 80 files to get your one change implemented for a given forecast to run appropriately. They need to be fully interoperable. It doesn't matter which app you're running the FE3 model in, it's always going to run with that same driver. It's going to be loosely coupled and stateless, meaning it doesn't really depend on other tasks that are running other than the data transfer that they need between them. It can also be stateless so that we don't depend on a previous iteration of that running before we get our information. We want to make sure that these tasks or services are responsible for one thing only. We can talk about what the size of that thing is or the scope, but it is clearly defined its responsibility. And then the standardized communication protocols are also important. So I've talked so far about those small tools or services, how we're going to bring them together under that service-oriented architecture, but how we approach that change is also important. I briefly mentioned the strangler pattern earlier as the approach that we'd like to take, and it's not quite as bad as it sounds, but it is named after the strangler fig plant, which essentially is growing around a host tree and then chokes it out, eventually replacing it entirely until you're left with something that looks like the tree, but it is entirely different. We want to do the same thing with this whole system, gradually replacing the existing system with the new services and the facade that allow us to do that. Think about the strangler facade sitting just under a user interface that is the new user interface, where the facade has a series of switches that allow us to go between the way that things previously have been done and the things that need to be replaced, the services for making initial conditions, running your forecast, or post-processing in this very simplistic overview. Maybe you get a few months into the project and you've worked out some way to do this better with your service, and midstream through the project, you could have a snapshot of this same facade who's turned on the switch to call the initial conditions and forecast services, but we still haven't quite figured out the post-process yet. We don't have to release that yet. We can still be pointing to the old way of doing things. There are some pros and cons to any approach that you're going to take to upgrading a legacy system, but I think that our pros here are going to outweigh our cons. Specifically, our benefits include that we can deliver this early. We can start to add that value early. We can iterate with end users to know that it's doing exactly what they need for their use cases, which can reduce risk associated with not delivering a complete system overhaul on day one. We don't have to do everything in the system from the get-go. And that's not just one system, but multiple numerical weather prediction systems. And then a service transition can be rolled back if we mess something up horribly. And then we can iterate as needed. What works, what doesn't, fix it in the next round for the next tool as well. And then we don't have to do all of the apps on the same schedule, which is really nice. There are going to be a lot of interfaces that make those switches from the old way of doing things to the new way. That's going to require a lot of attention to changes occurring both in our parts of the new system with services and in the original systems. And it can be very hard to modularize components that are tightly coupled. So here's what I mean. This is kind of the basic architecture of existing systems. Now, all of them follow this loosely, but they all have horribly different implementations so that it's not very consistent. Like if I, as a short range weather developer, want to move to using the hurricane analysis analysis and forecast system, I would have a huge learning curve just to understand how things are going here, but I would have a general idea of the architecture. Now, each of these layers are typically very tightly coupled with other layers, sometimes multiple ones. This configuration layer typically handles everything in the system. So how we're going to implement these switches between the interface with the workflow managers that we're not touching, we're just using in the compiled executables, for example, has a lot there to unfold. Let's talk just a second about that top layer, the configuration subsystem. I already gave an example of what it might look like to switch out different tasks, one weather model for another, one data assimilation approach for another. But here, the configuration subsystem is responsible for several things as well. It's going to be gathering user-provided parameters and managing those against default settings for various different portions of the system. And when I say default settings, these can be vast. There are a ton of different settings for each component of the system. We're talking the standards that you might think of with what input data are you using, what domain do you want to cover, what are the dates, what are the physics choices, all of the things that go into choosing your experiment. But then which components are you going to run and how do they interact with each other? And this is can go on and on. This is an actual diagram that we got out of that working group for the global workflow. All of these switches have to be managed. And in the current configuration system, they're all managed in a way that's coupled tightly with all other parts of the system. And then all of those can be defined by how we are defining the system that we want to run on. Is it one system? Is it multiple systems? In the case of, testing across those, does the system that you want to run on support these features? So we have lots to consider as these all interact with each other. If you can get that to all work appropriately, you're going to create your experiment directory in this configuration subsystem to stage the files and data needed for the experiment, and then maybe even start the workflow manager of choice. So here I just want to do a very brief demonstration of what I mean by decoupling between these configuration interfaces and the workflow definition, or maybe even a forecast driver. Something that we don't have currently is the object-oriented design pattern at all in our bash scripts, of course. So moving toward that so that we can then define a pretty loosely coupled system where we know that we need to validate things, but we need to validate what that individual thing needs and maybe cross-validate with other tasks. So let those classes be responsible for those validation tasks. A workflow knows what it needs as information to come in, so ask it what it needs. A forecast knows the resources that it's looking for on a given platform. It can tell you what its job card should look like, for example. It can also validate that input. It can create its own name list. Another thing that I think is important here for decoupling the workflow definition from the various different tasks that we might want to run in a workflow is to have these drivers be able to communicate back with the workflow to say, this is what I require, this is how I run, and this is what I'm going to give you if you do all of those things correctly. So if we have those three requirements on our drivers, we can start to even decouple from the workflow, which has not been something that's been easy in the past. So I do want to summarize here. We have identified that there are too many tightly coupled workflow systems in place currently for the UFS. We're going to get rid of that, hopefully, by building a unified framework that's built on standalone services and a service-oriented architecture pattern. And then we're going to take the strangler approach to replace the existing components gradually over the course of the coming years. I do want to mention that we have gotten started on this project. We are in that early development phase of releasing the first couple of tools. We have our GitHub repository here, along with wiki and discussions to make this as open as possible. Engagement is one of our key concerns here with making sure that we're taking care of the community's needs. And then we also have contributors guides and users guides to help the onboarding process for that. So please do feel free to stay in the loop, check us out there, and I can take any questions or suggestions or reach out to me later. Thanks.
Thanks, Christina. Again, for those who are attending remotely, feel free to put questions in the Slido. And then if you have a question here in the audience, yeah, looks like we have one already. So
All right. Good talk, Christina. I was just curious, most of your examples kind of like pre-processing for the model, like, getting things set up. Is there plans to do post-processing as well? Like even all the way to eventually scientists want plots and tables and stuff.
Absolutely. Yeah. So we do aim to capture all parts of the system, couple forecasts, even with other, ocean wave models, that sort of thing, but also on the side of, any portion of the system that we might want to interrogate our data with. So these were just samples for, but because I don't ever want to make that one diagram big to have to explain it. But yeah, everything in that diagram, I think, is up for grabs.
Okay. And have you kind of already made the planning decision of like sorry, I'm going to target on plotting specifically because there's kind of obviously lots of different tools out there and lots of different methods for generating plots.
Sure.
Has your team come into agreement of what you're using yet, or is that still kind of being decided?
So each app currently in UFS is going to make its own decision there. It's also going to make its own decision on what components run in general, right? HAFs will be slightly different than the short range weather app, for example. What we would like to see is that we've made a flexible enough system that you can plug in any component that meets this driver requirement to communicate with the system anytime. So maybe we're supporting some Python-based workflow thing, but if you can get your NCL graphics to run with that same architecture around the service, then there's no reason that can't go in as well, if that's what you would like.
All right, thanks.
Yeah.
I'll bring it too.
Thanks. Yeah, first off, great talk. Really interesting process that I didn't even actually recognize a lot of the things that we're kind of going through at our modeling center in the same way. We just didn't really put a lot of words to it. I guess I'm imagining kind of the strangler approach is to try to help keep things in production and also allow researchers to keep still working and doing their science while you're doing this big software refactor around it. I'm just curious on the process about how do you manage that interaction with kind of the researchers and people who are more focused on the operational side of it, just the outputs, or just they want to keep doing their research who might not necessarily be as, how do I want to say it, invested in the software approaches as you might think they should be. How do you kind of keep that from them still being able to do their science and their operational work that they need to do without kind of disrupting them to the point where they're like, well, I had this old system that worked for me. How do you keep managing those expectations?
That is the question. So our hope is that if we can continue to increase the funding for our team specifically, we can kind of embed our software engineers from our team on those development teams for those different apps to give them the resources they need to adopt this, to get their documentation updated, to kind of have a learning experience there in the process, so that we're not just forcing them into it, but also have the dedicated resources to help when something goes wrong. So that's one reason I'm still emphasizing funding sources and actual dollars to bring this to the different apps. Like we cannot rely on in-kind funding on all of this because funding changes regularly and priorities change regularly. So we need to make sure that we have that allocation there to help. It's not a full answer, but The best we've come up with yet.
All right, thanks again, Christina. I think we're at the time for the coffee break. Yeah, let's thank Christina again. All right, so just a reminder, yeah, we'll kind of resume at 10:40, so we should have about 25 minutes. There's stuff outside, refreshments. If you're remote, hopefully you at a good coffee shop or something like that, and you can virtually participate in that as well. So yeah, we'll resume at 10:40. Thanks.
Yes.
All right, so it is 10:40, and I think we'll go ahead and get ready for our next speaker. All right, so our next speaker will be Dr. Amit Ruhela from TAC, Texas Advanced Computing Center. And he is going to speak on containerization at Petascale on CPU and GPU HPC architectures. So Amit, take it away.
Thank you. My name is Amit Ruhela and I work at TAC. I'm a researcher there. And prior to joining TAC, I was a developer in MVP2 group at Ohio State University. So this is a joint work with some of my colleagues at TAC, Stephen Lian, Harrell, John Kazis, Todd Evans, and several others. This presentation is basically our experiences on containerization running at a large scale, running thousands of nodes. And in this presentation, I'll go briefly about what is containerization, why it is important in HPC, what are the containerization technologies that we explored, and then I'll show you the performance evaluation at baseline. So we basically baseline the performance at micro benchmark level and then run scientific applications to estimate the performance of containerization and compare it with bare metal runs. So what is containerization? Basically, containerization is a standard way of encapsulating software and its dependencies so that they can run uniformly across variety of systems, not just a system where they are built in, but they can run on variety of systems which are basically compatible with each other. So containerization has become popular with Docker's introduction in 2013, though the technology was there since 70s. So once the Docker came, they provided the technology they provide a way to run containerization on commodity infrastructures, and that changed the entire era. Right now, if we look at the containers in TAC, basically just for the bio containers, we have more than 4,000 or 6,000 containers just for bio applications. So there is a huge popularity of containers, and they have become popular because of the way they solve the they reduce the development life cycle, time of development life cycle. So prior to understanding the containerization, let's take a look at the virtual machines which were popular before that and how they are different from virtualization. So virtualization is basically a way of providing virtualization is basically a way where you can abstract the entire machine or a host, and you can have multiple machines running on a single host system. So they are basically, there is a layer called hypervisor. So there is a layer called hypervisor, which basically provide a way of which basically hides the, which basically provides a way to create multiple machines on a single system. So there could be two types of hypervisors. One which is basically sits on top of operating systems, host operating systems, and then you have virtual machines where each virtual machine contains the guest operating systems as shown here. So this is a type 2 hypervisor which is running on the host operating system. The other way could be the hypervisor running on the infrastructure, basically the hardware. And then we have a hypervisor layer, and on top of that, we have a virtual machines. Now the containers, they do have a similar kind of things. They bind the application, their dependencies, and they make a one container. However, they are different from virtual machines in the way that each virtual machine contains a guest operating system, which is quite large in size. So, and because of this, the virtual machines are quite heavyweight. They take more space. They have more. Since each virtual machine is basically a partition of partitions the entire memory as well as the resources. So they do not scale pretty well compared to the containers, which are very lightweight. They do not have their own operating systems. In fact, they share the operating systems with each other. So what are the benefits of containerization? The first is the portability. You write once and run it on multiple machines. And your code is like, you can have your own virtual machine. You can have your own system where you can build the containers and run it on variety of systems, or you can develop the container on HPC if the fake root is configured. The second is the scalability. So containers provide scalability because they are lightweight. They do not consume a lot of resources, and they can be run on thousands of nodes, and like full subscription. Like I ran containers of 56 processes per node, which is the highest PPN supported on our systems. Then the accessibility. So containers can be accessible from variety of platforms. For example, you can run it, you can just have it your own, or you can host it on the Docker Hub, Singularity Hub, or any other Amazon Hub websites. And anyone can download it from there. They can be downloaded on any systems using simple commands like Docker pull or Singularity pull, etc. Faster deployment. Since you don't need to spend a lot of time in identifying like what are the requirements of my target systems, so you can just write it once and deploy it on multiple systems. So they basically provide you an abstraction. They provide you an abstraction of running them on multiple machines. They do not use the software library. They do not use a lot of libraries from the host system, but they have their libraries integrated within the containers. So basically, they help in deploying the applications faster. Then the software choice. Just like TAC and other supercomputing systems, software choice is like a lot of users. We have thousands of users who have different software requirements. And as a HPC administrator, it's not possible to meet all the requirements. So containers are best in that case. Like they don't depend on the system libraries. They have their libraries integrated within the container, and that's why they can be run on any system. So you can build the containers for TAC and run on other systems as well. Large capacity. So HPC systems have a huge capacity. They have a huge thousands of nodes, and they have so many resources. So containers are quite popular, quite efficient in the way they can consume the system resources efficiently. They can speed. They are sometimes more efficient than the system libraries, and they can leverage those resources and provide you a solution, quick time to the solution of applications. So the goal of our research is basically to estimate what is the performance of containers on HPC environment, and what are the challenges and possible approaches to build the HPC clouds with container-based approaches. So there are 3 container options which we explored. We don't want to explore all of the options. We just want to baseline the performance with certain containers and see whether containers are useful in HPC. They have been useful in cloud environments, but we wanted to estimate the performance over HPC where we have thousands of nodes. So the first is the Docker, which is first popular implementation of containerization that started in 2014. Docker is written in Go language, and the Docker manifest file, which is basically a recipe of writing a containers, has become a industry standard industry standard specification for writing portable containers. Docker are not fit for HPC environment. The reason is that the Docker runs a daemon service which requires a root privileges to run on, and most of the HPC system, they don't provide the root access on compute nodes. So that's why Docker is not much popular in HPC, though there are some places, some institute they provide, but that is a risk, because providing a root access to a normal user is not desired. The second is Singularity. It's a Lawrence Berkeley National Laboratory project. Singularity uses the same Linux features like namespaces, CG groups for restricting the resource accesses, and union file systems. So Singularity is although based on the same concepts of Docker, but it doesn't require a daemon service, and therefore it can be run in a user space mode. Then we have a Charlie Cloud, which is another project which is similar to Singularity. When 2017, when Charlie Cloud was released, it was just 800 lines of code. Now I think it's around 8,000 lines of code. It is much more cleaner solution of Singularity, and I found certain times more efficient than Singularity. The systems, these are the hardware systems where we run our containers. We basically ran Singularity in Charlie Cloud, and we ran it on IBM Open Power systems, plus which was having NVIDIA V100 GPUs. So this was our Longhorn system, which is deprecated this year. The another system is AMD ROM. I think it was from Purdue. And then we have Intel Cascade system, our Frontera systems, and then the Intel Broadwell plus NVIDIA Quadro RTX 5000 GPUs. So here what I want to show is that I ran containers of a variety of systems, IBM versus Intel versus AMD. I ran it on CPU and GPUs, and I ran it on multiple interconnects like EDR100, HDR and all, or FDR56. These are the libraries and their versions which we use. Singularity, Charlie Cloud, MPI library, we use MVAP2 GDR and Intel MPI. Then we ran micro benchmarks which were already there in MPI libraries, and applications which is Milk and VPIC. So how we build the containers? We started with the base containers. So this is the main advantage. You can start with any base container which are hosted on a variety of systems. You just integrate your application within that. And we had a virtual machine. We downloaded this base containers, added our own application files, generated a new manifest file, and just build the container with one single command. So for Intel systems, we use these containers, the base containers from tech website. And for IBM Open Power systems, we use the IBM.com Power AI URL as a base image. And on top of that, we build the Milk and VPIC applications. And in all these runs, we use system MPI to launch the containers. So each container is having MPI within it, and there is another MPI which is outside the container, which is basically used to instantiate the containers. And after instantiation, only the MPI which is embedded in the application container was used. So let's start with the baseline performance. The most basic benchmark is MPI init, which what it does is it just run the MPI init command on all the containers, nothing else. Like it's just say that the container is MPI application is ready. So we compared this MPI init container on our tech systems. This is the Frontera system. We compared native is basically the bare metal performance, like running it natively on the system, and then the Charlie Cloud. So on the left side, so we calculate the total time in running the MPI init benchmark. It's not the time for MPI init operation, but it's the time to run the entire benchmark, which basically runs like 1,000 or maybe 10,000 times the MPI init operation. So we ran it on 64 nodes, 128, 256, up to 8,000 nodes. PPN is set to 1. PPN is processes per node, which means one container is instantiated on one container was instantiated on each node. As you can see, the performance till 2000, like here, they are almost like equal. The containers and bare metal run doesn't have any difference. But after 2000, I was seeing like container was showing me much better performance than the bare metal run. I suspect this was due to the MPI or the libraries which was integrated in the container. They are more efficient or tuned compared to the outside environment of the container. And that's why the bare metal run was taking more time. When I ran the same operations 2 years before, but on lesser number of nodes, like 6,000 nodes, container and bare metal runs were almost equal. I suspect this was due to non-tuned, or the system libraries were not tuned, and therefore the containers were having better performance than the bare metal runs. And this is surprising. This looks weird. Containers are having better performance, though they should show some kind of like instantiation or tear down overheads, but I didn't see that here. Then the next operation, then the next test was we carried out was comparing the performance at full subscription of a node. So in this every node we instantiated 56 containers. In total, we ran this operation till 458,000 processes, 458,000 containers. And as you can see, again, the containers were having better performance than bare metal runs, though the difference is not large. And it shows that containers can be efficiently used on any HPC systems. The second operation was the collective operations. The earlier one was MPI init, which is just like MPI init operation. Now I wanted to run a collective operation, which is a bcast. In this operation, one process or one container send a message to all other containers. I estimated the performance of bcast starting with one process per node, and as you can see, the latency at small message size somewhat higher for the Charlie cloud, but if you take in overall performance from starting from 1 byte to 2 raised to 18 byte, which is I think 512 kilobyte, or yeah. So if you can see, the performance of the Charlie cloud as well as bare metal runs are almost equivalent. This is the time for one bcast operation. But if you take a look at running the entire benchmark for thousands of iterations, this is shown in the right-hand side figure, and it shows that even at the 8,000 nodes, we just see the difference, which is MPI init difference, is shown in the previous graph. So whereas if you just discard this difference, otherwise bare metal and container runs are almost similar. The same experiment was run at full subscription. And the trend was similar, that containerized runs at full subscription of nodes have no significant performance overheads against bare metal runs. Then let's come to the applications. So the first application which we tried a lot of applications. I'm just showing the two applications, which is MIMD lattice computation, quantum chromodynamics code. And here we tried to estimate the time to solve the conjugate gradient solver. So this is one solver which is there in Milk, and also the total time to run the entire benchmark. We ran this benchmark from 17,000 containers to 140,000 containers, and as you can see, this is perfectly scaled well. So you can see that at all the scales, the performance of containers and bare metal runs are almost similar. We see small overheads, but this is not significant. Even in the Linux time, if you take a time to run the entire Milk benchmark, this benchmark was run for certain number of iterations, maybe 4 or 5, I think, yeah. But in actuality, Milk is run for several hours. I just ran it for a few minutes. I don't want to waste the system resources just to get the performance estimation. So even with this, we saw that the Charlie cloud and bare metal runs were having almost like similar performance trend, and the time in seconds was like not very much significantly different. And the next thing is the memory consumption. There is a common misbelief that containers have an overhead in memory, like they do consume memory. But if you take a look at this memory consumption, they're exactly similar. They don't take a lot of memory. They might be some few kilobytes or maybe some bytes, but not at very large scale. So memory consumption wise, they are similar. Time wise, they are similar. Then we ran this same benchmark on GPU nodes, and this is our Longhorn system. So we ran this container from 32 to 256 GPUs, and we measured the application time as well as memory consumption, which I found like almost exactly similar. The next application is vector particle in cell code. We ran it on CPU and GPU systems on AMD ROM, which is Purdue system, and Intel Cascade Lake which is our Frontera system. We kept the number of containers exactly similar to see if there is a performance difference across the machines or across the architectures. This experiment was run with Singularity, and earlier applications, earlier numbers were shown with Charlie Cloud. So here, as we can see, Singularity versus bare metal run, they almost have the same kind of performance. And we saw that performance of containerized runs is on par with bare metal runs. And even the architectural differences like AMD ROM versus Intel Cascade Lake, exactly the similar performance. Then we ran this vector particle and cell code on GPU nodes. This was IBM OpenPower NVIDIA V100 GPUs, our Longhorn system, and then Frontera RTX-Q, which is a RTX NVIDIA Quadro RTX 5000 nodes. So as you can see, the performance is exactly of some very minor differences are there between native runs and Singularity runs. Now, let's take a look at what are the lessons learned. So we recommend, based on our experiment, we recommend containerizations for any applications that have which has a complex build cycle and which is not easy to port on multiple systems. So containers definitely solve that issues. And containers usage is recommended to exploit massive tuning and optimizations realized within application containers. As I showed you in the previous slides, container runs were having better performance than bare metal runs, which is primarily due to the optimized libraries which were there in the containers. So you can always have higher versions of MPI or interconnect libraries or other libraries in the container in the application containers, and those may give you better performance. Containers majorly improve portability. This is true, but not true in all the sense. For example, containers built for Intel systems cannot run on IBM OpenPower systems. They also have issues like when you have diverse MPI implementations. For example, if the system library is Intel and the library which is installed in containers is quite different. For example, OpenMPI, there are sometimes compatibility issues. We also find compatibility issues with the different CUDA versions. The CUDA versions outside the container as well as within the containers, if they are not compatible, they might not run. Though we tried, we were successful in running one time on Quadro RTX, but we couldn't leverage the GPU features because even though library was compiled, application was compiled pretty well, but it was not able to exploit the GPUs. There are further several other issues could be glibc. If you are running, if your container is having a glibc which is pretty new, and if you're running on all the systems, that might not be compatible with each other, and it will give you a glibc incompatibility error. Containerization technology solve these issues. For example, Singularity solve these issues like bringing the system libraries to the container using -NV argument. If you provide that, it will use the system libraries. It will just add the CUDA libraries which are there in the system within the container. Same is with the Charlie Cloud. ch from host is a command which basically brings the CUDA libraries from the system to the containers. So they are working towards these portability issues, but they are not foolproof. Like you cannot think of like you can run on all kind of systems. You can run on certain kind of systems which are compatible with each other, and that is still pretty useful. Applications which have simple build instructions, I don't think like you need to have a container for every such application. If it is just like make install, you don't need a container for that. You just install it and use it natively on the system. Further, if there is a mission critical applications, the containers have very big issue. You cannot easily debug those containers. Containers run as a black box. You cannot, your tools, your debuggers, profilers, they cannot see what is happening inside the containers. And that is the reason, like I don't suggest anyone who has a mission critical applications don't use the containers, because it's not easy to debug. You'll not be able to identify what exactly is the bottleneck, where the application is failing. So if a application has a complex build cycle, definitely you have advantage of making a container out of it. Several users, several thousand users of tag, they use containers, and they use pretty efficiently. So these are the lessons which were learned. In summary, I can say that containerization majorly improves the build complexity of HPC applications. There are no significant overheads compared to bare metal runs, even while running at like 0.45 million running with 0.45 million containers on 8,000 nodes. There are no general security issues in HPC environment, though Docker has published some articles where the security issues were there. I think they have resolved it long back. Nothing we saw after that. And we validated this on-par performance of Singularity, Charlie Cloud, these two containers. I think we ran Podman as well also, but we didn't run it on large scale. So we ran it with Singularity and Charlie Cloud at extremely large scale, and we found that they have exactly or on-par performance with bare metal runs. So this is the summary. If I think I'm done, I'm happy to take your questions right now.
Are you familiar with the MPI trampoline library?
MPI?
MPI trampoline?
No, I don't know.
So there's this MPI trampoline library that I think the idea is, I don't know too much about it. I was just curious. So the idea is you build with an MPI implementation, and then it's kind of an interface to where at runtime, you can change the MPI implementation at runtime. I was just curious if anybody had any experience with that, if that would help containerization issues.
I haven't used the MPI trampoline library, but I have certain cases where I use the system MPI instead of the MPI within the container. The reason was like when I was running with the CUDA and I think on the GPU systems, the system MPI library, like I just bind mount the system MPI library onto the containers. So it's pretty standard, like you can use any library of your choice just by bind mounting those library within the container. So what you have to do is you just need to change your LD library path or path variables and then use them.
Yeah, I know that's one of MPI is like the big problem.
Yeah, it's a big problem. Like we saw it on, especially on IBM open power systems. But other systems, we tried both. Like we use system MPI, we use container MPI. There was not much difference. And many times, I think the MPI which was there within the containers, they showed better performance. So, yeah.
All right, so we have one question online, also MPI related. So this is from Brian Dobbins, and he says, do you have different MPI libraries in the native and Charlie Cloud environments? We've seen latency improvements in containers too, but only because of implementation differences, for example, eager limit size differences. It doesn't make much sense outside of that context to me, so I'm curious.
So does he mean multiple MPIs within a container? Is he saying like that?
Well, it's a Slido question, so it's not a
Okay.
back and forth, but I think it's just talking about like, you know, different external and different inside the container MPI libraries.
So MPI libraries outside and inside could be different. This is what we do, like we have done in our case. So outside we launched it with Intel MPI, and inside it was MWAPish2. So this was there. Do you have different libraries in the native and native? So yeah, we had a different MPI environments, different libraries in native and Charlie Cloud. The reason is, if you are building a container with Intel MPI is not openly available. So you might have to use MWAPish2 or MPish, which source code is available on their respective websites. So you can build that container with those libraries. So we tried all sort of combinations, having the same MPI library inside outside, having different MPI libraries inside outside, and each of these results seems to be done.
Yeah, I think we can probably do one more question real quick. So let's do, Timothy says, each of these results seem to run applications that initialize and use their own data completely within the container. If the application needs to access large data sets that are outside the container, would additional data movement latency issues be incurred versus bare metal?
No, I don't think so. The reason is you are again the bind mounting the outside environment, outside folder or directories within the container, and it's just a bind mount. So additional data movement, I don't think so. If even if you have a container running outside, or even if you have a container running, we just bind mount those directories within the container, and then they run it as just like the directories within the container itself. So there will not be additional data movement. Data movement would remain the same because containers they are totally ignorant to that because the directories are bind mounted. So I don't think so. This will be having this will incur more latencies. So yeah.
All right. All right. Well, I think we need to move on, but thank you, Amit.
Okay, thank you.
Yeah, feel free to follow up with Amit later if you have additional questions. All right. So welcome the next speaker up on the podium. And our next talk will be from Alper Altuntas from here at NCAR in CGD. And he will speak about verifying ParamGen, a case study in scientific software abstraction and modeling. So please take it away. Thank you.
How do you point? Is there a mouse or something? Hi everyone, my name is Alper Altuntas. I'm a software engineer here at NCAR at the Oceanography section, and I'll present this Python module that we call ParamGen. It's used within the context of climate modeling. We use it in CESM, our climate model here at NCAR. But more broadly, I'll talk about software verification and formal specification, which is describing a software system using a precise and high-level language. And I'll argue in this talk that formal specification can help us design maintainable and reliable scientific software. So the subject, ParamGen, is an infrastructure library to generate default input parameter files for Earth system modeling components. So these default input parameter files, they correspond to out-of-the-box model configurations that are determined by the model developers. And if you're familiar with CSM or SEAM, it's very similar to this nameless gen module, but there are a few advantages. First of all, it supports any format, not just Fortran nameless, and it supports any template format, not just XML. It's quite lightweight and generic. And it supports arbitrary Python expressions in these template files to specify parameters, parameter values, interdependencies, constraints among those parameters. So we've initially developed this lightweight module for MOM6 in CESM, and MOM6 is the new ocean component of the community Earth system model. And then we were incorporating MOM6 in CESM and felt a need for this ParamGen module. But more recently, it's started to being used by multiple CESM components. So this diagram summarizes how the ParamGen workflow works. Basically, on the left, we see a template. These templates are put together by the model developers, and they contain all the information for all possible cases. And ParamGen reads in this template, interprets it, and depending on some high-level configurations set by the user, it generates a model input file. And in this template, you'll see we have three variable definitions. The first one, NiHalo2, that's basically the simplest case where we have a key and a value. Key is the variable name, value is its value. In the second case, NiGlobal, we have this conditional branches. So depending on these Python expressions, NiGlobal will be set to 320 or 540. In the third case, diabetic first, we don't have conditional branches, but what we have as a value is this arbitrary Python expression that will determine the value of this variable. So here are some of the terms I'll be using. Here's an example of a template branch consisting of 3 lines. First line is the label. The second line is a guard, and the third line is the value for this particular entry. And labels and guards are similar. They are basically keys of key value pairs. The distinction is that labels are either strings or Python expressions that evaluate to strings, whereas guards are logical expressions that evaluate to true or false. And then these guards basically are propositions of values that determine which value gets picked. And all these types of entries can involve these expandable variables. And the way these expandable variables work is pretty much the same as how they work in shell scripting. Basically, ParamGen will replace these with their actual values. And so there are a few features of this module that make it quite flexible. First of all, these expandable variables and Python expressions can appear in anywhere in the template, labels, guards, or values. And there can be multiple labels along a branch. And that's useful when, for instance, we want to group these parameters into nameless groups, or we want to specify properties of parameters. And there can be multiple guards along a branch, and there's no restriction on the ordering of guards and labels. But there are a few schema rules. First of all, there must be at least one label along a branch. And if one of the keys at a particular level is a guard, all the keys at the same level must also be guards. On the left is a violation of this rule. Description is a label, and ocean grid equals G16, that's a guard. We cannot have labels and guards at the same level, but on the right is the correct specification of the same information. And so the main operation here is this reduce method, and the reduce method takes in that template, interprets it depending on those high-level settings determined by the user. It produces the final model input files. And then the way it works is it traverses all branches recursively, all the template branches, and it applies in-place modifications like expanding variables, evaluating those arbitrary Python expressions, and imposing those guards, logical expressions. And there are a few sources of complexities here. It's a recursive algorithm with in-place data modifications, so it's not that straightforward. And there's a lot of flexibility in the template layout because, so in this case, we will have a lot of template layouts and topologies that we need to consider in terms of reliability. And so we have a lot of testing in place. We do routine unit and integration tests, but testing is of course crucial, but it's not complete. We can use testing to show the presence of bugs, but never to show their absence. And oftentimes actually testing can fall short of showing presence of bugs too. So what can we do beyond testing? We can actually prove that our programs are correct. For instance, using formal methods. These are mathematically rigorous techniques and tools for specifying, designing, and verifying software. And in this talk, I'll be using one such method based on this tool called Alloy. It's an open source language and an analyzer for software modeling. It has an input language, a modeling language that's simple, precise, powerful, and I think very elegant. And this language allows us to model software and algorithms at a high level. And here, by high level, I mean at the design level and above the code level, about implementation specific details. So in the next few slides, I'll just briefly give a quick tour of the Alloy language. And so again, this is a software modeling and analysis tool. And its input language is declarative, combining first-order logic and relational calculus. And as scientific software developers, we are used to imperative programming paradigm, where we describe how a program does something in a step-by-step fashion, where these sequential statements change a program state. And then in the case of declarative programming paradigm, we describe what a program should accomplish, rather than providing a step-by-step recipe. And so there's no state changes or mutation. And that might sound actually limiting when we want to represent dynamic behavior, but there are a few mechanisms to represent dynamic behavior. In the case of Alloy, for instance, we can have this assignment of variable x to some value. Normally, we cannot reassign it because we can't have state changes, but we can use this prime operator to update the value of x at a virtual next state. And here I have this new value, that's the old value of x plus 1. But actually, in Alloy, I cannot use plus for integer arithmetics. What I should have used is this add function. And there's a fundamental reason, because in Alloy, everything is a set. So basically sets are first-class citizens, and common operators are reserved for set operations. So plus is set union, minus is set difference, etc. And these sets in Alloy models correspond to these abstract concepts that we have in our software. So, and we can introduce these sets or concepts using signature declarations. And here I have two examples, the value signature and key signature. Value signature is quite simple. It doesn't have anything special in its body, but the key signature here has this field called map, and it points to a value instance. And you can also think of these signatures as classes, like in the object-oriented languages. So this map field may be interpreted as actually class member, and I can actually use this dot operator to access any fields of any particular signature. So k.map, for instance, will return the value instance that this key instance maps to. And you can also interpret these as relations. So map field here is a relation from keys to values. And speaking of relations, we can also actually interpret everything as a relation in Alloy. It's based on relational calculus. And here are all the relational operators. And I'll just mention the first one, the arrow product. And we can use this arrow product operator to refer to a relation between sets. Assume that P and Q are sets of some signatures. And P arrow of Q is every combination of tuples of members of P and Q. And I can restrict multiplicities in these arrow product operations. For instance, here I have this lone keyword, which means less than or equal to 1. And here, P arrow lone Q means each member of set P maps to 0 or 1 member of set Q. And I can also have multi-iterative relations. I'm not limited to binary relations. And so that was a quick tour of Alloy. Let's move on to the ParamGen model in Alloy. And I'll also mention how these models may be used for verifying the correctness of our software and algorithms. And here's a typical workflow to follow when we want to model a system in Alloy in an agile and incremental model development style. First, we specify the structure using those signature declarations, then specify the dynamic behavior and relations among those structures. And then at that point, we end up with basically a full model of Alloy, and we can instruct Alloy to generate model instances, and we can visually inspect those instances and might identify some design flaws that's not apparent initially, and then we can go back to the model, eliminate those design flaws, and as a final step, we can actually also analyze these models in an exhaustive manner, rigorously. So I'll begin with the structure of ParamGen, and I'll represent it in Alloy using signature declarations. And the main ParamGen structure, data structure, is this template notion. And in ParamGen, internally, these are stored in nested Python dictionaries. And in these Python dictionaries, keys may be those labels or guards, depending on the type that they evaluate to. In the case of strings, they are labels. In the case of Booleans, they are guards. And the values here are either variable values or dictionaries in the case of Python dictionaries or nested dictionaries. And so here's my abstract representation of dictionaries. So Alloy is a simple language. It doesn't have compound data structures like hash tables or Python dictionaries. So I'm representing dictionaries in an abstract manner here. The first signature is the dictionary signature with a field contents, and that's set of keys. Dictionary contains a set of keys. And then the key is defined in the second block here. It has a field called map, and it's a variable map, so it can change over time. And I have the value signature here. So the key signature, you'll notice that it's abstract. And so I can go ahead and extend that key signature with these 3 derivations, or it's basically, this is like class inheritance. I'm inheriting from those, inheriting from the base key signature and introducing these new 3 derived key signatures, label, guard, and root. And then the root here has a specific constraint that basically says that it cannot be contained by any other dictionaries or any other items. And at this point, I have this full model, and I can generate an instance that satisfies this model. And here's one such instance. And I can visually inspect this and see if I have missed anything in my model. So dictionary 0 here is the outer dictionary containing label 2 that maps to dictionary 1. And dictionary 2 and dictionary 1 here contains the same label object. That's one flaw here. And then label 0 and label 1 map to the same value object, another similar flaw. So I go back to the model, add these constraints, and these constraints involve some relational operations, some quantifiers, and set theory operations. I won't go into the details of these alloy specifications moving forward, and I'll just mention what they mean. In this case, the first one says that each item can have at most one key. In the second case, each key can be owned by one dictionary. So I'm eliminating those two issues I've identified. Here's a new instance Alloy automatically generates. These are arbitrary instances, and Alloy can generate multiple of these. And so I don't have those two issues anymore. If I go back, but I have another issue. So in this the outer dictionary, I have two labels and a guard. And as you might remember from the schema slide, we cannot mix and match labels and guards. So I go back again, add this new constraint saying that dictionary, if one of the dictionary keys is a guard, all dictionary keys must also be guards. So I go through this iterative process of adding constraints, looking at instances, and I end up with this full list of constraints, and I group these in a predicate definition that I happen to call invariants. And predicates are basically Boolean functions that return true or false. So that was pretty much the whole structure in an abstract manner. Now I'm moving on to the dynamics. On the left is the Alloy model of this main reduce operation. On the right is the Python version. And so as you can see, it looks quite similar. At least the structure is the same. The syntax is obviously different. But the reason the structure is the same is currently we are at this high level, algorithm design level. And all the implementation specific details are hidden behind these function calls, impose guards and expand bars. So let's compare those functions. So here's a comparison of impose guards in Alloy on the left, in the actual Python implementation on the right. And at this point, you see some significant differences because we are getting into the weeds, getting into some implementation specific details. And more strikingly, here's the comparison of expand bars. This is, so again, on the left is the Alloy version, on the right is the actual Python implementation. And in the Python implementation, you can see all sorts of string manipulations, regular expressions, for loops, if statements, etc. Whereas the Alloy version just states what should be accomplished here rather than step-by-step recipe. And this abstract representation of these lower level details can allow us to focus on high level software and algorithm design aspects. And that means quick prototyping and early detection of design flaws. And this also actually allows for incremental modeling. We can go back to the code or the model and add more and more details as we need. And here's a quote from a well-known article, No Silver Bullet. The hard part of building software is the specification, design, and testing of conceptual construct, not the labor of representing it, not the labor of implementing it. And along the same lines, here's a more recent quote. What matters is the fundamental structure of the code. If you get the design wrong, then there's no amount of bug fixing or refactoring that will produce a reliable, maintainable, and usable system. So going back to the Alloy model, here's another instance. This time we have this dynamic behavior of going from an initial state to the final state as a result of calling the reduce method. But I won't go into the details of that instance. What I'll instead do is I'll actually instruct the Alloy analyzer to check for pretty much all possible cases within a given bound. And so it's called bounded model checking. And Alloy will generate pretty much all possible topologies, all possible template layouts, and all possible state transitions automatically in a given bound, of course, and then it'll exhaustively check for any violations of my safety conditions that I specify. And here's all my safety conditions. You'll notice the first one here is the invariance that I've initially specified, and I want to know that those invariants still remain true, but I have also a bunch of other safety conditions that I want to make sure that holds at all times. So Alloy goes through that, generates the whole state space, exhaustively looks for counterexamples, and at the end tells me that there's no counterexample and that my assertions may be valid. So this is quite useful. It's exhaustive, rigorous, and gives me a lot of information about the safety of my design. But there's also another fundamental advantage of this way of designing a software, and that specifying a system helps us understand it. As Leslie Lampert says, specifying a system will help us understand it, understand the systems that we build, and it's a good idea to understand the system before building it. So it's a good idea to write a specification of a system before implementing it. Again, along the same lines, Daniel Jackson says that code is a poor medium for exploring abstractions. And my interpretation of this code is that before starting to code, we should actually form our abstractions, our concepts, our software design, because when we start coding, it's too late to well form those abstractions, well form those relations between our structures in the code. But this way of development may not always be feasible in scientific software realm, because sometimes we are handed over pre-developed code for integration. Sometimes we underestimate complexities or project targets change. And oftentimes we work with the legacy code. So, but still, I think specification and modeling may be useful at later stages of development as well. And in fact, this study is one such case. I've modeled ParamGen in Alloy after I actually developed ParamGen, but still it helped me better understand it, going through that modeling exercise. And after going through that exercise, I was able to go back to the code, refactor this reduce method, and basically ended up with a lot more clear code. And I was able to also identify some flaws in the template handling and sanity checks. And that was the result of this modeling exercise. And in summary, so formal specification and software modeling may help us develop reliable software and maintainable and efficient software. So as for reliability, testing is crucial, but incomplete. And formal methods may be complementary to testing. It's not a silver bullet, but it might be useful in some cases. And as for maintainability, we, the scientists and engineers, are accustomed to working with models anyway. So that's what we do on a day-to-day basis. We work with abstract concepts. We develop designs based on those abstractions. And with automatic push-button analysis features like Alloy provides, we can actually focus on modeling and design aspects, initially at least. And those design aspects matter more so than lower-level implementation details in the long run for reliable and maintainable software. And before I conclude, I'll make a quick announcement. We are organizing a workshop on correctness and reproducibility for climate and weather software this November, and it'll be at the NCAR Mesa Lab. If you're interested in these topics, please visit this webpage and perhaps consider submitting an abstract or registering. With that, I'll conclude.
You. Do we have any questions in the room?
Thanks, Alper. It was a great talk. Yeah, putting up this last slide actually is a good segue to my question. So it was really cool seeing you model ParamGen with Alloy and using Alloy to sort of abstract that piece of software and then formally verifying it. Sort of makes sense to me in the scope of like a parser, right? And trying to like get it to parse, make sure that you're going to parse all these possible templates correctly. And it has me wondering how something like Alloy could apply to something like, yeah, verifying correctness and reproducibility for something more complex like climate and weather software. Is this something that, you know, is being investigated or is going to be discussed here? Or, you know, what are the limits basically to modeling more complex pieces of software like this and verifying them?
Yeah, so there are actually a lot of popular formal methods tools. Alloy is one of them, and the strength of Alloy is in terms of relations between the structures of our software design. But there are other tools that might be more suitable for, you know, a climate modeling context. For instance, there's this TLA plus tool that's very good at capturing concurrency. For instance, if you want to model some concurrent behavior, Alloy might not be the best tool, but there are tools out there that might be more suitable to the problem that you target. So yeah, again, in the realm of formal methods, there is not a silver bullet. You know, there's not a single tool that will work for everything, and formal methods itself won't work for everything. But I think it's worth exploring those tools out there and see if there's any benefit in using it for, you know, these intricate design stuff, or, you know, for lower level stuff as well. There are a lot of tools and techniques to, you know, reason about your code or design.
Great, thank you.
Let me walk back here and just check online. Yeah, we do have one question online. Can you employ Alloy as a form of static code analysis within CI/CD as well? When you add a feature, for example, you have an equivalent Alloy abstraction, so as part of like a CI pipeline.
I'm not sure if Alloy is the best tool for that. There are a lot of static code analysis tools based on formal methods, based on similar approaches. But my initial reaction is that Alloy might not be the best tool for static code analysis within CI, because it has its own GUI that you model and analyze your design. So yeah, but this, you know, broader idea of having a formal methods tool to statically check your code within CI/CD, that's perfectly feasible, but Alloy might not be the best tool for that.
Thank you. Yeah, that question was from Andrew Show. And I guess maybe I'll have a follow-on question. You know, I wasn't familiar with Alloy, so I appreciate the primer. As you like, so you sort of, you went, you had an existing code and then you modeled it in Alloy. Are there tools to sort of do that translational work of the system, or is that a pretty manual process to go from the Alloy, you know, model of the system to the code itself?
I think there are tools that extract models from codes. Alloy is not one of them, but so I mentioned that one of the advantages of Alloy is that it allows you to rigorously check your design. But another benefit is that it helps you better understand the code that you're developing. I think that's a significant benefit. And if you automate that step, you're losing that understanding. So yeah.
Makes sense. Any other questions? Yeah.
Thanks, Alper. Obviously, for a lot of scientific codes, we kind of don't know the behavior, or at least that's why we're doing that in the first place. But, you know, maybe is there a way to then use these tools to kind of apply, trying to think of the right word, but like, you know, sort of scale analysis or asymptotic analysis where you say, well, I don't know how the behavior of, say, the ocean's going to do, but I know if I put, you know, if I make it below 0, it better forms sea ice or something. Like, is there a way to kind of do that sort of testing, particularly for climate and weather scenarios?
Yeah, I might not exactly answer your question, but there are, you know, there's another tool that I've used in the past that actually does analysis for hybrid systems where we have discrete and continuous system at the same time. So, you have this continuous evolution of ocean, let's say, and at some exact point, you need to have this discrete behavior of going to the ice, right? So there are tools that you can allow you to model and analyze that kind of behavior.
Awesome, great, thanks.
Yeah.
All right, thanks again, Alper. We're going
Thank
to
you.
move to the last talk. Yeah, our final talk before lunch will be from John Rood from National Renewable Energy Laboratory, just down the road. And he will present Spack-Manager, which is reducing scientific software development overhead through Spack. So take it away.
Am I just pressing this button? Yeah, okay. I guess you already did the introduction for me. I guess, but before I worked at NRL2, I just mentioned that I worked at Mateo Swiss in Switzerland doing weather and climate. If anybody wants to talk about weather and climate, we can do that. So yeah, I'm going to talk about Spack-Manager, which is really like a couple of extensions we've added to Spack, the Spack package manager. I hope most of the people in here know about Spack. I've been using Spack for about 10 years, so I feel like I'm a little bit far away from actually just getting into Spack and learning Spack. So if you haven't looked at Spack, I think that you should. So it's a package manager that's mostly ingrained into HPC. You don't need to, you can do it outside of HPC, but it's pretty focused on HPC. So you can see, so actually I list my colleague Philip Sakovich here first because I stole these slides from him, and he's basically the main author of Spack-Manager. I do a lot of work in the packages and stuff, but he's like a core developer of Spack. So he really made this for us. So you can see this directed acyclic graph I have here of the application that I'm going to talk about that we use Spack-Manager mostly for. So Spack's really fulfilling all these dependencies for us in this application and building all this software for us. So I'm going to give you a little slight overview of the Exawind software that kind of motivated this work, philosophies that led to Spack-Manager, a bit of the organization of Spack-Manager. The key thing that we use Spack for is software development. That Spack kind of started out as more of an administrator thing, but using Spack for software development on a complex application is very great. It's fantastic to use these days. So we'll talk about some of the infrastructure of that. And we also have some administrative tasks in Spack-Manager that we use as well. One really cool one that I'll talk about too. And some, we do container work and like nightly testing in Spack-Manager. So my motivating application is Exawind. So I'm funded under the Exascale computing project. And the Exawind software stack is extremely complicated. It essentially combines two loosely coupled CFD codes. So Trilinos, which is what really makes our DAG large. So we have this Naluwind application that does the turbine mesh. And then in between that, we do an atmospheric boundary layer between the turbines, and that's an AMRX code. AMRX is an adaptive mesh library out of Berkeley Lab. So we have AMR Wind that does our ABLs. So we're developing a lot of other software. So we have about, I think it's seven packages that we are actively developing. We have the Exawind driver, Naluwind, Trilinos, AMR Wind, Tioga couples. It does a hole cutting between the two domains. Hyper does our linear solves, and OpenFast actually does the turbine loads on the wings because the meshes can deform. So we're all actively developing these at the same time. Living on the development branch of those. So, and we also program on CPU, and the Exascale computing project is trying to program on GPUs mainly. So we do performance portability in there, and we're using several different machines. So we have to build this large stack on several different machines. So you can see all the challenges we have there, everything. So the Spack package manager I talked about before, Spack really leads us, all this stuff leads us to using Spack. Because it's really going to resolve the dependencies for us and build all the packages for us. So there's a lot of attractive features. It's got a lot of HPC knowledge. It has a unique scalable multi-component development tool called Spack Develop that I'll talk about. But using Spack does have some challenges. It's really, Spack is a large international project now, so it moves slow and fast at the same time. It's pretty sensitive to changes. If you dealt with Spack before, you know that the concretizer is the solver to solve the dependencies, and there's a lot of stuff that goes on. That's a very large computer science problem in itself. So some of the philosophies behind Spack-Manager, it's really just an extension, and we do write Spack-Manager. We try to write Spack-Manager as an extension to Spack. So we're writing actual Python Spack code like it's a core, but you can write it as an extension, and then we try to push our stuff into Spack over time. Like Phil has added the way to check out Git commits on the command line. So that was a thing that started in Spack-Manager that we pushed into Spack. So one of the key things we do, or actually, what do I want to say here? So yeah, this is a framework to prototype new Spack features. In Spack-Manager, a crucial thing that I feel like you need to do in development is manage machine-specific configurations. And Spack-Manager really kind of automates injecting those configurations into our Spack environment when we use our Spack-Manager commands. So Spack-Manager is trying to unify the workflow for administrators, which ends up to be basically me and Phil. And then there's a bunch of application developers on the team, and then end users. And if you look on the right side, there's like an inverse relationship between how much Spack you need to know based on where you're at. So end users don't need to know anything. We can just deploy modules to them. Application developers kind of need to know how to use Spack developed features. And admins, we have heavy Spack knowledge, and we need to know a lot of the ins and outs of Spack. So here's the layout of Spack-Manager. So the yellow on the right, we have like predefined locations where we put in Spack environments. We deploy modules in a specific area, and views are basically where you can take a bunch of different directories all over the place and kind of unify them into a single directory structure. We have a bunch of scripting in the middle there where Spack-Manager actually lives with the commands, and we have unit tests. We actually unit test Spack-Manager because Spack is very testable. On the left side, we actually submodule Spack itself, so we can keep track of this commit of Spack that we're on. We have some scripts, and then one of the key things here is the machine configs. So we're developing machine config. Whenever we show up on a new machine, we can develop, we want to use the MPI on the machine, so we can do our configuration so that we don't build MPI ourselves. We just pull the MPI from the machine. And we also have custom package repos for Spack. So when you're working on a project like this, you always, in my opinion, need to do very specific things for depending on what machine you're on. So once we know what machine we're on, based on the specific packages, we can do specific things that we need to on the machine. And those can never really go back into Spack, unfortunately. So this is kind of the vision. We have the daily build environment. That's essentially just like the core of Spack-Manager. We do our nightly tests through Spack-Manager. We really just run a Spack install command, and it populates the nightly tests. I'll kind of show that stuff. Every night we build a Docker image that runs GitHub CI. We can create modules to deploy for end user analysis. And then the developer workflow on the right is based on all of it. And the developers can actually create their own modules. And if they're working on a feature, they can just expose the modules that they've generated to end user analysis, and they can use those modules. So the idea is we're all kind of building the exact same thing. Depending on what machine we're on, we're all on the same page. So yeah, Spack-Manager really attempts to do a machine agnostic API. So we have a bunch of machine specific configurations, but everything beyond that is kind of generic to whatever machine you're on. So essentially Spack-Manager is really trying to curate environments for you and inject all the configuration in there for that machine and for the project. And right now we're very specific to Exawin, but we're trying to break out to just do general projects is our goal. So you can look at, if you were using Spack on the right side, the things you would have to do to actually start building Spack or building packages in an environment. So you can create the environment, activate the environment, activate your local repo of packages that have specific customizations for your project. Then you manually insert the machine specific configurations. There's packages YAML file, configs YAML file, compilers YAML. There's more than that, there's modules.yaml. And then you do Spack add, so you add all your packages that you want to build. And then you can deactivate the environment. So Spack-Manager really kind of rolls all this stuff into single commands. So on the left, we just do Spack-Manager create env -d is basically the name of the environment, and then -s specs. Specs in Spack are really just the packages that you want to build and the options that you want to build for those packages. So this is what it looks like. I don't know if you can see this text too well. Maybe people online can see it easier. But on the left side, we have a spack.yaml file, which really has the packages that we want to build listed in the specs. So I have exawind, AMRwind, and naluwind. And then I have this include statement that includes a YAML file. And on the right side is that include.yaml. So that's the thing that Spack-Manager created for us in the environment when we did the create env. So it pulls in things like the repo that we want is we want an extra layer of a repo for packages that we've customized. We have a list of packages and our preferences for these packages. If you look at Trilinos, there's a million variants that we want to select, so we can minimize the build time. And we can do things like pick where we want to cache our downloads, where we want the build stage to be, so where the scratch space that Spack will build in. So we have a list of features that Spack-Manager or some commands. So create env, the convenience script that we have for making a Spack environment. Create dev env, so you're going to make a developer environment, and that's where when you list the specs, now you list the specs and you basically clone those repos and you have the source code local. So once you modify code in there and then do Spack install, now it's building from your code that you've modified. Because usually Spack will download a tar file, build it, and then throw everything away when it's done. So develop really keeps that around. Find machine is crucial to interrogating which machine you're on. We have Python code that just looks for, descriptive factors on the machine and tells you which machine you're on. And then we have this external command that I'm going to talk about a little bit later. So when you're developing with Spack-Manager, so this is key. I really want people to understand how powerful this is, like based on this slide. So in a Spack environment, develop specs can be added. So what that means is, like I said, when you do a Spack develop and then add the package that you want to develop, you can look at the specs over on the right side here. So I have naluwind plus CUDA with the CUDA arch, so I'm doing V100s. naluwind minus CUDA, I have those in both of those in my environment. And then if you look at this red, the develop specs, so that means that I want the naluwind source code and the Trilinos source code. And when I do Spack install, I want Spack to install using those. And when I do Spack install, naluwind will build both with plus CUDA and a separate nalu based on the hat. So Spack will kind of create a hash for each spec that you've installed. So in my environment, I can do naluwind for the GPU and naluwind on the CPU basically at the same time. So when I do Spack install, it will install those both for me at the same time. And I hope people realize how powerful that is when you're developing an application on the CPU and the GPU, that you can do those concurrently. And not only does it build those for you, Spack has parallelism in the graph, in the DAG. So you can do Spack install twice or 50 times. And Spack uses file locks, so it will build naluwind plus CUDA and naluwind minus CUDA concurrently. So that's very useful for building quick. So Spack develop, amazingly powerful. Setting up a development environment can be a lot of work. It can be pretty tedious, so Spack-Manager really aims to reduce the number of commands. Here's a little insight on how it kind of like a workflow that kind of works on the right side. So we just have a start.sh script, so we source start.sh. And then you could do Spack-Manager, create env, list all the packages that you want to install, activate that environment, and then you can switch any one of those to Spack develop to develop specs. So I want to develop do, re, mi package at the same time. And then I can cd into any of those directories, change the branch that I want to build, and do all the things underneath there until I do a Spack install, and then it will just install with that source code. So on top of Spack-Manager commands, we have some bash functions that really do a lot of shortcuts for you. So common features are, we have this Spack start feature. So, okay, we have quick create on the left column, quick create dev on the middle, and then quick develop on the right side. So they each add on like an extra thing that they do to short circuit. So we have the Spack start, which will actually invoke the Spack into your shell, because we don't do that by default because it's slow to kind of activate Spack. So we want it to be fast until we want to use it. So quick create, I'll create an environment, activate the environment, and add root specs just based on doing a quick create and then listing the specs that you want to have. It'll do all those steps for you. Quick create dev will basically do those as develop specs because you want to develop them. And then quick develop will also add externals. So it will try to help not rebuild a bunch of third-party libraries underneath. So I might talk more about that one later. So this has been really great for us in onboarding developers. So we've made significant efforts to help people build this, to build Exawind. Developers, we have to ask them to learn some Spack, even though Spack does get a little bit complicated for people, but we've really had a lot of buy-in for our project for this. You're not developing Exawind without using Spack-Manager, and nobody really complains about it, which has been great for us. This is our third iteration of a build system. We started with Spack, then we had this thing called Exawind Builder, and just along the way, we've just iterated on to Spack-Manager, and has really kind of solved everything for us. So in my opinion, you can see me up in the upper right hand. I really think it's made us an order of magnitude more efficient in developing. And you can see we have some testimonials from AMD and CMD. So here's a key thing to mention is the way that we do externals. There's a bunch of ways that Spack can reuse binaries, so you're not building stuff all the time. So you can upstream multiple Spack installations together. So if I have one Spack, I can say, hey, look at this Spack and see if stuff's already built. You can use binary caches where you download basically off the internet of binaries that people have already used. You can do Spack, you can issue -- reuse to the concretizer and have Spack aggressively try to reuse packages that are already installed. But all three of those rely on the concretizer to make the decision for you, where we use externals. Like I mentioned before, if I want to use the MPI on the machine, I just tell Spack that I want to use that. So for the externals in Spack-Manager, we basically make all our third-party libraries able to be generated as an externals file. So at that point, you can list buildable equals false into each package, and then Spack will not build that package for you. So you can guarantee that Spack won't build these, and it will use the externals that we created. So yeah, we basically use this to make snapshots of our code over time. So we have time-dated versions of the software installed on any particular machine. And then developers can hook into those externals, and then they really only have to build the top-level packages. So here's an example of what I've used to debug a memory leak. So, you know, we're developing 7 codes or whatever, and we had this memory leak hang out somewhere in the code over about a year, and nobody ever sat down to do it. So I finally sat down to do it, and this is exactly what I did. Quick develop, and then I list 5 top-level packages that I'm certain the memory leak is in one of these. And we have this variant called ASAN, which is the address sanitizer, which is much better than Valgrind, because Valgrind will never let you complete your run, but address sanitizer will. So I list the CMake build type as debug. These are all CMake packages, so it's fine to do that here. And then I want to use the Clang 10 compiler. So I do quick develop and I set up my environment, and then I just say Spack install, and it installs all that with all the options. I CD into the Exawind directory, and then I run ctest on Exawind, doing Spack build env, so it loads the build environment that everything was built in. And then I just run the tests, and now I have address sanitizer on for all 5 of these top-level applications. So I'm hoping to see something. So I wait and see output. There's memory leaked, and I look at the backtrace and I see it's in Tioga, the overset hole cutter. So I go and edit the code. I find out that there's stuff that isn't being freed, and I just edit the code. Now I do Spack install again, and now it just does an iterative build. It doesn't have to rebuild everything. The source code's already there, so it's going to link things that are already built. But my code, it's going to rebuild the file that I changed, and then relink. and then I can go to the build environment and then run the test again, and I can just iterate on that. So at the end of the day, it's really just relinking and it's doing an iterative build. A big problem with this is if your link time is very long, it doesn't help you very much. So if we're on the frontier machine at OLCF, Exolin takes 3 hours to link. So that's a problem that we haven't solved yet, because no matter what you change, you're waiting 3 hours to see how it, if you did it. Anyway, so pros and cons of Spack-driven development. Spack is solving the dependency issues for us. The DAG parallelism is huge for us. You can see that I did a test where if we didn't have DAG parallelism, 4.5 hours without to build Exolin on a machine, 1.5 hours with. We can do plus CUDA and minus CUDA in the same environment. You can do that with all the variants. Spack is testable. The unified API is great. Spack is overwhelming to some people. The build process has some quirks. The hash-based reductions really can cause confusion. There's still some optimization to do. Spack isn't the best at doing the iterative builds, but I think it could be better over time. I'm trying to cruise through some of this. So because I do want to get to, I think I might skip this. This is basically, so we used to have an old test script, and we started to make packages for the nightly builds. So in our custom repo, we have like an AMR win dash nightly test. So that really does all of the C test and C dash stuff for us. So that allows us to just do a Spack install, and then it runs it builds and runs the test automatically for you. So that's all encapsulated into like Spack itself. So when we did that, there's a little line down here that says our test script, our generalized test script really went from 500 lines to 100 lines at that point when we switched to Spack-Manager. So I'm going to skip some of this stuff because I really want to talk about this extra little thing that we started to do in Spack-Manager. So this is credit to Harman Stoppels, who's like a core developer of Spack from Zurich. And I just want to mention that at NREL, I have a LDRD, so Lab Directed Research and Development money to work on this the rest of the year. So this is something that we're invested in. So if anybody's interested in this technique, I'm really interested in talking or advertising this to people. So one thing you do when you show up to a machine, and this is, you know, mostly for administrators, but you show up to a machine and you get GCC 8.5 or 4.8, 4.85 or whatever. And now you want to build a bunch of stuff on top of it. So you typically have to do a bootstrap phase where you like make a base compiler like GCC 8, install binutil so you can get a linker that'll link to an updated like Skylake AVX 512 machine or something. And then you want to build on top of that a bunch of compilers that you want to use, LLVM, Intel. And then on top of one of those compilers you pick, maybe Clang 15 or something, now you want to build an MPI implementation, CUDA on top of there, and HDF5, NetCDF, all that type of stuff. So Harman Stoppels designed a way to use a makefile with Spack to automate all three of these phases. So you can really just use what they call Spack dep files and show up in a directory, and you can just type make, and once you know you have all your configuration set up, but it'll do all three of these phases automatically for you, which has been a huge time saver. So I've used this at NREL on a machine that's been erased on us twice without them asking us. So it's been, and you can see the line that I did after I cloned Spack-Manager, I have this line on top that really built all of these modules for me automatically, starting from a GCC 4.85 on a bare metal machine. So I have all the compilers down at the bottom, and then I built everything on GCC 10. You can see all the packages there. So another thing we've done is use containers. So we partner with E4S, the extreme scientific software stack. There's 4 S's in there. I don't remember what they all are, but so they build a container for us every night that has the entire Exolin DAG built in a container. And we can use that based on our externals like technology in Spack-Manager to do CI for Naluin and all these things that would take a lot of time to build all of the software underneath it. So the text in our GitHub CI is really small on the bottom there, but you can see I have Spack-Manager commands. There's just like 4 of them, 4 or 5 of them that do the full testing for us and the C test suite on Nalu, AMRWin, and Exolin for us, all with this single container that our externals let us do. And developers can download this and they can develop on their laptops. We also, I mentioned it before, we made packages specifically for testing with C-. So we have like Spack install Exawin nightly. We'll build and run and then submit the test results to the C-. And you can see we just have this YAML file that has all our nightly test specs in it and all the stuff we want to build with it. So if I have Clang, I'll turn the address sanitizer on for all the packages that I want, and then I can see if there's memory leaks now in lower level packages. And that really the single Spack install generates this whole, and our dashboard's a mess, but it generates all of this for Nalu on GPUs, Nalu on CPUs, AMR win on GPUs, AMR win on CPUs, all of that. So we're very happy with Spack as the driver for like all phases of our DevOps process in Exawind. It's really dramatically reduced the infrastructure needs. A lot of the developers, they have the tools, they know how to customize their own environments. And it's really helped them learn Spack too along the way by us trying to minimize the overhead for them. And I think that they can move into other areas of projects with Spack and feel comfortable. So we think the cons of Spack can really be mitigated with just education and a few assumptions and light scripts to get people started. Yeah, we do extensions in Spack directly, so we write Python code directly. What else? So yeah, just the Spack-Manager is one example of how this should be done. And we're looking to share and like generalize how Spack-Manager is, but I just hope people take the things that we've done and realize that you can do this stuff with Spack. Obviously, where we'd like to go next is to add more applications that aren't Exawind. Exawind's a pretty shining example because of how complicated it is. I assume that, you know, weather and climate couple a lot of codes together, so hopefully they could utilize stuff like this. We need to clean up the code and generalize it. We want to improve testing infrastructure to be able to test Spack-Manager more. And sometimes you know, Spack will change things over time that really cause confusion for us. So it's hard to be to really track Spack as well as we want to. And we do like to upstream our features to Spack. We don't have a whole lot of time to do it these days, but it takes a lot of work to upstream features to Spack because it's so international and generalized. So I think that's all my slides. Thanks.
Thanks, John. I could ask you a lot of questions, but I'll hold off and see. Does anybody in the room have any questions for John?
Hi, John. Thanks. Great talk. I'm Eric Lingerfeld. I'm with the JEDI program, and we use Spack as well for everything. It's a magnificent tool. One thing I was wondering about Spack-Manager, do you guys ever, when you deploy something locally, let's say on like Mac OS, how do you guys handle conflicts with externally installed tools? A simple example would be like Python 3.11 installed with Brew, but your particular application wants Python 3.10.
Well, Spack likes to resolve Python itself. So even though we have Python installed, you will see Spack, you know, we won't list Python as an external. We will just use Python to run Spack initially based on whatever Python 3 is available. But Spack will go through and resolve whatever Python dependency it wants and use that one. So at that point, it's not using the Python that we started with, I guess. So hopefully that answers the question.
Any other questions? All right, then I'll ask a simple one. So the makefile approach that you had mentioned, is that specific to Spack-Manager or is that using core Spack functionality?
No, it started out in Spack-Manager. I just wanted to advertise it essentially, but I've broken that out. It's super simple technique, honestly. That's a makefile and just a list of configurations that you like YAML files that you've already created for machines. But essentially, yeah, if anybody's interested, I just show you the makefile, and it's pretty cool to see how Spack, just in a single Spack instance, it will create multiple environments and install each one of those phases in a separate environment. So, so yeah, that's how it works there. But you don't need any of the Spack-Manager infrastructure to do it. I've broken it out into a separate project for my LDRD that I mentioned that I'll be working on the rest of the years.
All right, thanks. Oh yeah, one more question.
In terms of going forward, do you see this merging with Spack or the development like right
So
now?
yeah, since Phil, who is the author of Spack-Manager, is like a core developer of Spack, he's definitely upstream stuff already. We don't have a lot of time to do it, but we do have, I forget, there's a couple features of that Greg Becker, who's a developer on Spack, if people are familiar, has asked us to upstream to Spack as well. I don't remember exactly which one it is, but yeah, the idea is to try to generalize as much as we can. You know, we can't do a lot of, like, we couldn't do the find machine command necessarily because Spack doesn't, like, it can't really, it shouldn't tell what machine it's necessarily on. It knows the target architectures and stuff, but that's something that's very crucial in my opinion, that you need to know what machine you're on based on what project you're on. So you have to do customizations no matter what. You try to get around them, but you have to. So there's a lot of things we can upstream, but we definitely try to generalize and upstream as much as we can.
All right, thanks, John. And let's thank all the speakers for the morning session. Thanks to you all for your attention. So yeah, now we have an hour break for lunch, and we will resume, I guess, yeah, 1:10. So see you back in the room, hopefully, and for those folks online, we'll see you back on the Zoom. So have a good lunch.
Okay. Okay. All right. So let's go ahead and get started. It's 1:10, so we should get started on the next block of the afternoon talks. We have two speakers coming to the next talk called Buildtest, a framework for testing HPC systems by Shahzeb Siddiqui and Prathmesh, Sambrekar. So we'll go ahead and get started with these talks, and I'll hand it over to our speakers. Thank you.
Can you hear me? Okay, good. All right. Yeah, I'd like to thank the organizers for hosting this event. Yeah, it's a great opportunity to be here. Unfortunately, I couldn't be there in person. And considering that it's now in person, yeah, I was there 2 years ago. Everything was remote, so glad to see people there in person. Hopefully, I'll be there next time. So my name is Shahzeb Siddiqui. I work at Lawrence Berkeley National Lab. One of my colleagues, Prathmesh Sambrekar, he's at Arizona State University, also an intern here at Berkeley Lab. And today we'll be talking about Buildtest. So we've given this talk in previous year. So we'll change it up slightly for some of you that may have never heard of Buildtest. What we'll do is actually at the start, we're going to actually give you a brief demo. So that for those of you that don't know Buildtest, you'll get to see what it actually looks like, and then we'll just kind of give you a little bit of some of the features that we have and how we use Buildtest. Okay, so let me go to the next. So I'll just give a kind of like what is Buildtest for those of you that don't know. It is a testing framework that builds and executes tests on your HPC systems, and you know, test could be anything that you want to really test on an HPC system. It could be the software stack, it could be your system environment configuration, you know, any kind of stuff like make, CMake, whatever you want to do. It's intended for the HPC staff the developers and even end users to basically write tests that you would do to verify your system state or the software. The project is open source. It's on GitHub. On the right, you see the documentation. It's on Read the Docs. And the way Buildtest works is it's basically tests are written in declarative YAML syntax, and these are called build specs. And Buildtest, what it does is it will just create shell scripts and run them on your HPC system. It could be on your login nodes, it could be on your compute nodes, and submit the jobs. We have integration with LSF, Slurm, PBS, and Cobalt, and the framework's implemented in Python. So with that, I'm going to give it to Prathmesh for a demo. Take it away.
So yeah, let's start with a quick demo. Can you give me a quick heads up to let me know if this text is visible on the screen?
Yes, we can see it.
Okay. Yeah. So once you have your Buildtest installed in your system, you can run Buildtest -- help command, and it gives you a list of commands and optional arguments that you can run. So you can use this to test if the commands are running. Next, let's see how to build a test. So to build a test, you can use Buildtest build -b option followed by the part with the buildspec file. So once you run this, yeah, you can see the Discord build specs listed here. Then these build specs are passed and validated with the JSON schema, and then they are built and run. So you can see the status of the test as pass or fail here, and also the return code along with other metadata. So now you also can run multiple tests by appending with -p option. You can build by individual buildspec file or by directories. So here I'm building an individual buildspec file called hello world, and then followed by a directory. So the configuration directory includes multiple buildspecs, and so all the buildspecs in the directory will be built now. So yeah, so now let's say you want to exclude a build spec. So you can do that by using the -x option. So you can exclude an individual build spec or an entire directory of build specs. So here I'm excluding the ulimits.yaml file. You can see the -x option here. So once you run this, you can see the excluded build specs here along with the Discord build specs. Now you also have an option to build your test by using different tags. So you can do that by running buildtest build -t. -t is the alias for the tags command, and I'm using a Python tag here. So it should be followed by a tag name. So you can see that it discovers the build specs which have the tag as Python. You can see it here. You can get the different tags available by just pressing tab after the -t command. So it lists all the tags available here. So next, let's see how to query the test report. So all your test runs are kept in a JSON file, and that's the report file. So to fetch all the test runs, you can run buildtest report command, and it gives you a long list of tests. So the output is too long to see. So you can use the -- pager option to scroll through your rows of the table. So yeah, you can see that it gives you the names of the tests and the test metadata and the part with the buildspec file. So you can scroll through the rows. Next, let's say you want to fetch all the failed tests. So you can use buildtest -fail. So here RT is the alias for the report command. And this lists all the failed tests. And now if you want to get the row count of the failed tests, so that for that you can just do dash row count, and it gives you the count of failed tests. So there are 142 failed tests. Similarly, you can do the same thing for past tests. Now to get the summary of the report file, you can use Buildtest RT summary, and it gives you the total number of tests available in the report file and the total number of tests by unique names, followed by the number of build specs in the report file. So next, you can filter through your tests by using the Buildtest RT digest filter option. So it accepts a key value pair. So we are using a so I'm using the tags as key and system as value, and you can format your table columns by using the dash format option. So once you run this, you can see all the tests are filtered using the system tags, and the columns are formatted with name, ID, and tags as mentioned here after the format option. Next, let's see how to inspect a test. So you can use Buildtest inspect command to display test metadata and query the test records. So you can use Buildtest ID name followed by the test name. So ID is the inspect for the alias for the inspect command. So you can use this command to see the raw JSON record from the report file. So it gives you the raw JSON record, which contains the metadata. Now, let's say you want to query the test record. So for that, you can use Buildtest ID query command. So here you can use -o option to get the content of the output file. So you can see the content of the output file is hello world, and it contains the other metadata also. So similarly, you can get the output of the error file by just using -e option. And yeah, there's no error, so there's nothing in the error file. So to get the content of the test file itself, you can do -t. Yeah, you can see the content of the test file here. It's just equal hello world. So let's see how to interact with the build specs. So you can interact with the build specs by querying the build spec cache. So to query the build spec cache, first you need to build the cache. So you can do that by running Buildtest build spec find. The -- rebuild option is used whenever you make any changes to the build spec. So you need to rebuild your cache. So it's building the cache now. And once the cache is built, it lists all the tests available in the cache. So this is a long list. Yeah. So it gives you all the tests available along with the metadata and the description of each test. It gives it here. Now, let's say you want to view the content of the build spec file. So for that, you can use Buildtest PC show. So BC is the alias for the build spec command, followed by the build spec file names. So you can view multiple build specs. So now, to get the summary of the build spec cache, you can use Buildtest build spec summary. Yeah. So this command gives a list of all the tests. It breaks down by tags, executors, maintainers, and it shows all the invalid build specs here. And then it also shows the test breakdown by build specs. So this particular build spec, it has 5 tests, and they are listed here. Now, also you can view your invalid build spec by doing Buildtest PC find invalid. So it lists all the invalid build specs from the cache, and also it shows the exception that has occurred. Yeah. So this was a short demo, and the next part will be continued by Shahzeb.
Thanks, Prathmesh. Okay. So I hope you guys had a kind of a good flavor of what Buildtest actually is. I'm just going to give a little summary about the project itself. So this project started in February 2017. It was originally a shell script where it basically was just trying to test very small set of software, and then it later converted to Python 2 and then Python 3. As of today, there's 44 releases, and there is some of the recent features that we've added is, for instance, we added performance check, and also like file checks, where performance check. We'll talk about these, but you can run tests and get metrics, and then run some performance tests on them. We added support for Spack support in version 0.10, meaning installing packages from Spack, meaning writing tests for like Spack where you install, you can test and do all sorts of other things. Adding batch scheduler support for like Slurm and LSF. The releases are updated and documented in our changelog and its MIT license. The documentation is based on Sphinx. And hosted on Read the Docs platform. Okay, so I want to give you a little bit of some of the design goals behind Buildtest. So as you saw in the demo, Buildtest basically tries to automate the whole test generation and execution process. So there's no that's one of the main goals is like we want to be able to automate this whole process where you can run the test, but not just that, but just also query the test, inspect the results of the output, the error, the test content, and also generating those shell scripts so that you don't have to write them yourself, right? It needs to have integration with HPC environment. That includes the batch scheduler modules, like for us, create programming environment. So we are, we have support for that too. And then obviously to lower the barrier for writing tests. So we intentionally picked YAML because it's really easy to use, and there is this kind of configuration kind of format where you can kind of specify the details, and then the test is written into a shell script. So we'll talk a little bit about the test pipeline. So when Prathmesh showed the execution of the test using Buildtest build, what typically goes in each of those tests is kind of this pipeline where first you discover the build specs, which is finding out based on the search criteria. That could be file, directory, tags, or executor. So that's the -B option or the -T tags. We have other options too. Next, it will validate those build specs with the JSON schema. So that's in the parse stage where we make sure that the test conforms to the schema. Then we build the shell script. So that's taking the YAML file and actually creating a shell script. This could be bash, it could be CSH, it could be any kind of shell script, but it typically defaults bash. Then we run the test, which typically is either you run it on local login node, or it could be a batch scheduler. And in this process, we're actually running the test, retrieving the return code, output error file. And then after that, then we do the sanity check, which it's dependent on the test, but you can perform sanity check, any kind of sanity check, but at the end, it will give you a pass or fail. So in the output, when you saw those pass or fails, that's what the sanity check is doing. And then finally, we update the report. That's what in the demo when you saw Prathmesh when he was doing build test report and all those queries, it's updated in this report file, and then you can query it. So we'll talk about some of the ways on how you write tests. So this is kind of like this overview of the build spec. So the way you start out with build specs is so since it's YAML, you have to know YAML. Build specs is the declaration of one or more tests. Under it, you define the name of the test. So the name of the test is systemd default target. You have to define a couple other fields within the scope of the test, that being the executor and then the type. The executor tells where the test needs to be run. The type is the schema type because we support multiple schema types, and that's used for validating the test. The script schema, basically think of it as your is a schema used for writing shell scripts. So in the schema, you're supposed to use run, which is a required property, and in that you can write any kind of shell script you want, like bash or CSH or whatever. Okay, so I talked about the status check in the pipeline, which is in the sanity check. The end goal is that the test needs to have some kind of state after running. So, to determine if the test pass or fail. We don't impose this rule because we let the users decide what needs to be done for pass or fail. But by default, if you run any tests on a Linux system, you can do it by return code. 0 is a pass, anything else is a fail, right? So if no status check is applied, that's what we use. But you can do other kinds of things like return code matching, regular expression search on any files, runtime matching, like, run a test, see if it compares within the runtime. You can do file check, you can do performance check. You can also do file count. So like, I'll talk about that. And then you can explicitly declare a test. Like, let's say, a test is going to fail, just mark it as a fail or a pass, right? So we'll talk about some of the new features. So file check, the way it works is, let's say you run a test and you want to know if some existence of a directory or a file. You can do this. So the Buildtest can support for directory checks, files, and also symbolic links. So I have this test I have two tests. If you look at the yellow, under status, you can declare your status check, and there's multiple keys. Is directory basically is just a list of assertions for if there are directories and if they exist. And if all of them are true, then the test will pass. In this home.bashrc is not a directory, it's supposed to be a file. So that's why this test fails. If you look at the output and the arrow, we even show the output. It's checking if each one's a directory or a file. And then, the second test is just basically combining them. So you can also use is file. So if you just move the home.bashrc to is file, then this test is going to pass. So I talk about performance check. So the idea is that we can try to run a test and perform some kind of regression test by doing some kind of comparison operator. Like this could be currently right now, the ones we support are all the equality operations, greater, less than, equals, and then not equals. And yeah, we'll talk about some of them. So for this example, what I'll show you is a basically like running the stream benchmark. If you ever run the stream benchmark, like, you can, well, I guess you can get the source code. It's available on GitHub. This is stream.c, and then you can compile it with like, let's say GCC or something, and then run the stream benchmark. In order to run the stream benchmark, if you were going to do like the performance check, we capture metrics, and the output typically has 4 things like copy, scale, add, and triad. And what you want to take away is that we're defining each metric by running a regular expression, like you see this regex on the output file. And then those metrics are assigned those values. Obviously, you have to know what the output looks like. And then in the status assert GE under line 38, we can specify the name of the metric and then the reference value. So in the output, when you see this metric copy, it's checking if it's greater than the reference value, which is like 5,000, 5,500, 6,000. And if those checks are true, then this test will pass. If any of them are false, then the test will fail. So that's the idea. We can also do equality check. This is a very simple example, but the idea is that, we're going to, so we have 4 variables defined under vars. So under line 6, you can see those X, Y, first and last. And then we're just going to echo these variables. and apply the metrics to get those metrics, and then we're just going to compare them. And if any of them fail, then it will fail. The thing about equality check is that we can also do comparison on strings, whereas the other operators they're only on numbers like integers or floating points. We also support test dependency. So the idea is that you can run tests out of order. This is using needs, but the idea is you can have like job A, job B, and job C. Job A has no dependency, job B has a dependency on job A, and job C has a dependency on A and B. So I'll talk about some of the new features. File count is one feature that was requested by one of the users. So the idea was he's going to run a test and he wants to count the number of files in a particular directory and make sure that that number, whatever it is a criteria for pass. So we added support for file count. It expects a directory and then a count, which is the reference count for comparison. So in this first test, we're creating 5 files, and then you can do file count by extensions. So you can have like, filter by extension name. So like .sh, the depth controls the traversal of the directory walk. So if you don't specify it, will just do the whole thing. And then the extension can also be a list. So that's the idea. With file count, since you can do multiple directory traversals, if you specify multiple lists, then it would do the assertion is logically ended. If that makes sense. And then you can combine for more powerful like regular expression search. So you're not just limited to like extensions. So for example, on the one on the left, we can filter by file type, so like directory or symlinks. These are just keywords, or you could specify file, and it will just kind of filter by them. And then you can also do regular expression using file pattern. So given a directory, the file pattern, what it will do is it will search for every single file that conforms to that expression. And then if it does, it will retrieve it. And that makes sense. And then you can also combine with like, let's say extensions. So you can have file pattern and extension. So like get all txt files and then get all like conf.py or main.py. And then obviously the sum is, you have to figure out what the sum is. It will return all of them. And then another feature is file regular expression. So let's say you run a test and you append it to some arbitrary file. And now you want to look at this file and see if the output matches the regular expression. We can do that using file regex. Previously, we didn't have this support. The only thing that we had support was for standard out and standard error. But with file regex, I have a test where I say echo hello to hello.txt and then Buildtest help in Buildtest help.txt. And then you can specify those files and then apply the expression. So I'll talk about how we use Buildtest at Nurse. So it's kind of give you an idea, like if you're wondering like how anyone could use it like at an institution. So we have a Git repository on our GitLab server. It's called Buildtest Nurse. The Git repository is basically just used to run tests, primarily focused on testing our software stack. That's called E4S, but we also run other kinds of tests. There is this repo is on our GitLab server, software.nurse.gov. There is a mirror on GitHub. And the way it works is we basically use GitLab CI/CD via schedule pipeline. So you see it on the bottom, where basically we're running a different subset of tests on different machines. So we have tests on Perlmutter and tests on Muller. We have our own GitLab runner, and all tests are run on the devel branch, and then tests get published to C-. So I'll show you what it looks like. This is the pipeline. You can press play, it will run the test, and then at the output of once the test completes, we run Buildtest C-upload, which is basically a built-in command that uploads all the reports to a C-, and then you'll get a link, and then you can view all the test results over there. So what are we testing? Applications like things that come from E4S, like Amrex, Cocos, like HPC Toolkit. We test other things like compilers. We even test things from Spack-Test. We test some system tools, user environments, things like modules, Spack, startup environments, system check like Slurm, file system checks like GPFS, Stream, etc. And yeah, if you need help, these are the links. If you have a feature in mind, please feel free to open an issue. We also have a Slack channel. There's a whole contributing guide. And yeah, and also in case you know, we publish all of our like conference talks. We even have tutorials. You can actually find them all under conference section right here. So in case if you're interested in actually seeing how we've done it in the past, we'll be actually doing another tutorial in Perk. That's it. Thank you for your time.
Okie dokie. Thank you so much. It was a great talk. I think we have, yeah, let's get it up. Thank you. If you, we have time for maybe one quick, brief question. Otherwise, if there are questions in the audience, maybe we could connect with the authors directly. You sure it's not brief? There are Slido questions. Let's see. Let's double check on that. Go ahead. Yeah, come on up.
Hey, thanks for the talk. I just have a quick question. So it looks a lot to me like GitHub Actions type YAML files. Do we know if GitHub Actions kind of open sources the stuff that they have for using, you know, GitHub Actions CI/CD? Because it seems like if you could get your hands on that, you could kind of take advantage of a lot of stuff that they've done.
Yeah, I did try to look at GitHub workflows as kind of like how they've done it, but I don't know if they have I guess like a published JSON schema. I mean, that was the one main thing, is like understanding how they've actually done their schema to write the thing, but yeah.
Well,
it is similar.
Yeah,
like
nice.
the jobs is similar. Like you specify jobs, and then a list of jobs is equivalent to build specs with a list of tests. Yeah, like the needs was kind of like there's a mix between GitLab and GitHub. Like I use the needs from I think it's GitLab. Yeah, I'm not sure. Yeah, like for job dependency, but yeah.
Yeah, it's nice if you're used to GitHub Actions. Then it looks like this looks pretty similar.
I am.
Okay, thank you so much. All right, one more round of applause for the presentation. Thank you. Okay, we're going to go to the next talk. And the good news is that one of the previous speakers will continue. So Shahzeb Siddiqui will present Lmodule, Python API for testing modules. And I'm going to hand the time to you.
Okay, thank you. Yeah, so this talk is going to be on Lmodule. Just to give you a little history, Lmodule was actually, it was part of Buildtest as a feature. The idea is like we're going to be testing modules, and then we decided, well, yeah, I think it might be beneficial if you just take it out of Buildtest and make it as a standalone Python API, so that anyone can actually benefit from it. So I'll actually be talking about, so when we're talking about module, we're talking about modules that you see, like module files on your system, and you want to test them, just to be clear. And Lmodule is just basically an API. So this is, so yeah, let's get started. So I want to give a brief survey that was done several years ago by EasyBuild user community. They have these surveys that they run like kind of every year. And what you want to kind of take away is that the survey shows that there is widespread usage of modules. And if you look at the number of, let's say, participants that responded, like about 49% had 100 to 100, like 100 to 1,000 modules, and then 37% had more than 1,000 plus modules. I mean, Easy Build generates lots of modules anyways. Spack does the same thing. So, how can we assure that these modules are working correctly, right? Like you need to test them, right? Like module load test every single one. And, like with automated module testing, like, we can kind of quickly detect problems with modules in production, obviously, reduce like, user tickets. So that was kind of the idea behind this, because module load is just a very basic thing, but if it breaks for everyone, and then you get all sorts of issues reported. So Lmodule is basically Python API for testing modules. Mostly it's focused on Lmod. It's available on it's open source, available on GitHub, and documentations on Read the Docs. And the way Lmodule works is it uses the Lmod spider tool to find all the modules. So yeah. So for those of you that may be familiar with Lmod, hopefully, kind of what we have mimicked is that there is a module command that you know of. So we have three main classes. One is the module class, which is kind of mimicking the module command. Then there is the spider class, which is utilizing the spider utility from Lmod. And then there is this special module load test class, which is basically automating the entire module load test for an entire software stack. So I'll talk a little bit about each of these classes and some of the ways that you could use these. And yeah, so some examples. So, you can import the module class. And then the way the module class works is you can specify a list of names of the module. So you can say like GCC core, and then you can use the get command to retrieve the actual module command. So it will run module purge and then module load. You can specify a list of modules. So it could be a list or a string. And then if you do get commands, then it will just do the module load for each of them individually. If you do test modules, then it will actually test the modules and give you a return code. So 0 means that it passed. Anything else is a fail. And then you can do some other things, right? Oh, sorry. You can also just invoke the module class without specifying any modules and then say isAvail, which is equivalent to the module isAvail command. What it shows is if the module is available, and it will be a return code. So we're checking if GCC is available and if CUDA is available. You can also change the way module purge behavior works. So if in a HPC system, you can load modules from a starting environment, which is your startup profile, right? Like you log in and then you have either some modules loaded. If you run module purge, it will erase everything and then you can load. The idea with purging is that it ensures that you're in some kind of clean state, right? If you just module load consistently, then you don't know if things are going to break over time. So purge equals true or false can determine if you want to do the module purge. That's kind of the idea. If you use force equals true, then it will do force purge. Force is just an option, -- force. That will ensure that modules like sticky modules are also removed. And then you can also, just an example, like if you do purge equals false and then force equals true, then it's not going to do anything because the force command is only used with purge. That makes sense. So you can also do things like user collections. Lmod supports things like, you can save modules in a collection using module save. You can show collection, using module describe, and then also module restore to actually restore from the collection. So let's say you invoke, so B is just an instance of module, right? And then you can invoke the save, and then it will save the modules in the collection. And then if you can also specify the name of the collection name. So let's say GCC zlib, and it will save these two modules in the collection name. And then you can also use the describe method. So by default, if you don't specify any arguments, it will just kind of show you the default collection. And yeah, and then the describe can be used to specify the name of the collection name. So like let's say GCC zlib. You can also use the get collection method, which will retrieve the restore command for a given collection, right? And then you can specify the name of the collection name. So it's just showing you the command that you actually are going to run. So the idea is like you can use this if you're going to be scripting, or you can just take it as a print statement or whatever. And then the test collection is used to test the collection, which is basically just running the actual command that you see, like module restore, whatever. The test collection can also specify the name of the collection name. So there is another method, method called get user collection. You could just import this. The idea is that the get user collection will list all the collection names. So, I'm just showing you the output here. I have a default GCC inside org. And the idea is like, let's say you want to test all the collections. This is really easy to do. You can just do a for loop over the collections, specify the module, like module A is a module, and then you can, I'm just doing test collection right here. Test collection, I is the collection name, and then I'm just getting 3 different commands like restore command and a return code. And then if you do a print, I can basically, the output is showing you the command that's being run, module restore, and then the return code. So yeah. You can also do the spider command. So meaning module spider. So if you do like m.spider, you can specify like GCC in Python, and then the output will show you kind of the output of that. The spider can also be a list or a string. If it's a string, you can do space separated, whatever. And then if you want, you can print the output. We added a new feature. So for those of you that have new version of Lmod, there was a module overview command. So I added a feature called overview in 0.4. And the way it works is you can invoke the module class and then just call the overview, and then you can call overview with the name of the module, and then it will just filter the output. It's just basically an equivalent to saying module overview, name of the command. That's basically it. Now we'll talk to about the next class, which is the spider class. You can do lmod.spider import spider, and then it has some of the features that it has is you can get unique software, get the module trees, you can retrieve the module names. You can also retrieve the parent modules, meaning modules that set module path to other directories. And then you can also get versions of all the software. So I'll talk about some of them. So you can just invoke the spider class. So if you look here in the middle, s.getNames, it will just show you the list of all the module names. And then you can also specify the spider to a specific directory if you want to just filter by directory. So the spider, what it's doing is actually, by default, it will just do everything, which is everything in module path. But if you specify the argument, this is basically just filtering by module path. That makes sense. You can do other interesting things like you can filter modules with spider. So if you want to look at this example on the top right hand, we use the spider class to retrieve all the modules, and then we can use so and then use the get modules method, which is built into Spider, which just filters out modules by names. So let's say I want to filter by GCC and CUDA. And what it will basically will show you is when you run the script, it will just run the module purge, module load. At the end, you're getting a name of a module, and then you can invoke it into the module class and then run test module. So just this very simple line of like few lines of code can test all your CUDA modules and your GCC module. This leads a good segue to the module load test class, which is basically intended to try to test your entire module stack. So this is only compatible with Lmod because it leverages the Spider command. And some of the features that it includes is it can test modules by module path. It can test modules by specific tree. It can alter the module purge behavior. So, and also filter modules by name. You can also set a threshold. So if you don't want to run all the tests, you can set it to some limit that you want. So to use this class, you just import the module load test, and then you can just go ahead and just run module load test, and it will run everything. So on an HPC system, you know, you may just want to run it once just to see how it is, and it will give you all the modules that are in your system, and then test every single one, and it will show you the output pass or failed. And it will show you the name of the module and then the full path to the module file. We can alter the behavior of the purge, and this is totally optional. You know, if you prefer that each module be tested module purge and module load, you can just say purge equals true. So, and then you can also specify the path to the directory. So let's say you want to specify the directory. I think I want to send to a directory and just test like in this core directory. You can do that too. The debug equals true can be used if you want to just see like debug messages, but it will kind of show you the actual command that's being run and the return code. So that's pretty useful. And then yeah, if you look at the output on the top and the bottom, with purge equals true and purge equals false, the difference is whether you want to run module purge or not. By default, I mean, it really depends on your environment, but on a Cray system, doing module purge may not be a good idea, but you know, it depends on your system. You can also test modules in a login shell. So if you set login equals true, it will basically run a command in a new login shell. So it will run like with bash L, bash within bash L. If not, it would just be in a subshell. This can be useful. I think, but I think recommendation is to do it in a login shell. But you know, you can filter modules by name. So name is just a list of names, you know, the canonical names. So let's just say we're testing all CUDA modules, and there you go. It will find basically module load test will just figure out based on the output of Spider all the modules, and it's obviously just going to see all the available modules and then test every single one individually. You can also filter and exclude. So you're not just limited to the names, which only works on canonical names. The include works on full names of the module, meaning the name / version. So if you use include, you can hard code a specific module that you want to test. And then you can also do exclude. So include works first and then exclude are done after inclusion. So let's say you want to do module load tests on an entire directory. This is user share Lmod. If you know of this directory, this is the installation of Lmod, which typically comes with 2 module files called Lmod and setarg. So there's 2 tests. And then if I run exclude on Lmod, I will only run setarg. So the idea is that you can use exclude on, let's say, an entire directory, and then just specify ones that you don't want to run or you can do exclude like with names and then say like all the CUDA modules and then exclude one of them. Does that make sense? And then one recent feature that was added was, well, you have all these tests that you run with module load test. I want to get some test results from them. So then we didn't have this. So then I added a feature called get results method. You just can invoke it after running module load test. So it will basically just return a dictionary of number of passed, failed, and total tests, and then the rate, which is the percentage, passed divided by total. So so you can use those as a way of like if you're running a test on your system and say like your test passes like at like 95% rate, that you can do that. There is limited support for environment modules. The focus is primarily on Lmod. But if you're interested, like for instance, running module load tests on environment modules, it's not possible, though there is a potential solution that we have. There's a source file for this that kind of imitates this on environment modules, if you're interested. So I'll talk a little bit about the project and I'm going to conclude. So the project has regression tests, just like any open source project. And the way we test this is we're testing multiple versions of Lmod and Python. So you can, on the bottom, you can see kind of our regression test workflow. We're testing on 3.7, 3.8, and 3.9 of Python versions, and then kind of different versions of Lmod. If you know Robert McClay, he has like 300 releases of Lmod, so we can't really reliably test every single Lmod version. So I just picked some major versions to pick like one version from Lmod 7 and then one from like 8.6 and 8.7. Reason why I picked 8.6 is because they added support for module overview. And then all these test results get pushed to CodeCup. So you can see our test is pretty close. We're at like 98%. So it should work pretty well. So I just conclude here. So modules are kind of like primary interface between users and the software stack. So it is important to actually test this software stack. And, I don't know how many sites are actually doing this, but, if you can test it pre-production before putting it into production, you can probably avoid having all these user tickets that come in. And it also just doesn't set a good impression, right? And you come in and then users find broken modules. That's not really good. Lmodule provides like a simple Python API. So all you need is just a little bit of Python experience, and then you can kind of test any of these modules. And if you need help, there is a GitHub, so you can open up issues. We also have a Slack channel. And just wanted to kind of get some thoughts. If you have any feedback, like what features would you like to add support for, like thinking about it from the module perspective, and is there like an interest in like Python API for environment modules, like similar to Lmodule, but Lmodule is focused mostly on Lmod, but environment modules is completely different, like the way it's set up. And thank you for your time. These are just some references. Yeah.
All right, great. So there is one Slido question, and if there are any questions here in the audience as well, please feel free to step up to the microphone. Let me go ahead and read the one Slido question and see if you can answer this. So the question is from Amit. It says, great utility, Shahzeb. What do you test with this library? Format of modules, missing broken links in modules, module dependencies, runtime test, etc.
I take it you're talking about in the actual regression test that we run. Yes. So we are testing. Basically, the way it's set up is we're testing. We're testing all the features of the module, like the module class, the spider class, and the module load test class. So we just have like a directory of some dummy module files, and these are run on the system. So we are testing, like, let's say, the module load. We are testing features like, is it available? Like module is available, the module spider, things like the spider class, like getting like all the names of the modules, running the module load test. So that's what we're doing. The idea is basically to ensure that that the API is well tested to increase the code coverage. I hope that helps answer it.
Okay, thanks.
Yeah, so I think this looks really nice, and to me it looks like it would catch 90-95% of the problems you might run into. A couple of maybe subtle issues that I've run into before testing our module tree. One is something that works in Bash, but say doesn't work in C shell. If you have some, like setting a shell alias or a shell function in a module, that can be tricky. And then another one is, there are some edge cases where you set something in a module, but because the logic is such, it doesn't get unset when you purge. Do you have any thoughts on testing sort of those cases where you have like either, I guess you could call it environment contamination from your module, or just shell differences? Would that fit in the scope of this at some point?
Yeah, I think that at least to answer your first question about the shell, I think having support for login shell for different types of shell does make sense. I forget where it is. We might just have to have a different name. Yeah, like here we just said login equals true, but if you look at the output, it's probably not here. This one, yeah. So we're running with a bash. I don't know if you had like another option like shell equals C shell or Z shell. I've actually run some of these tests with different shells of the same test, but they work with bash, but they don't work with Z shell. So, I mean, that could be possible. If the shell is not available, then I don't know, we could raise an exception. And your second question was about. What was your second question? It was about environment contamination, right?
Yeah, I guess it's, if you have like a situation where you load a module and then unload it and the environment doesn't revert back to the environment that it was before the initial load, that's kind of a tricky module failure, but it can cause subtle application problems for the end user. So, maybe that's too complicated to test with this framework, or it's kind of out of scope, but
Yeah.
I just, what are your thoughts on that? Thanks.
I think that it could be possible, but I mean, if you were to write it as like a program, like a Python program, and I'll just give an example. Let's say you do module load, some like CUDA, and you're checking if an environment exists, and then you unload it, and then you can write some Python code to say if this environment is not present, that you could probably test some of this. At the moment, the module class doesn't have a module unload. That could be also another feature. Does that make sense? Right now, we're just doing module load. I don't know how you would want that feature, like if you want to load the module and then unload it right after. Or do you assume that you just unload it? It's kind of a question of how you want that. But I think these are valid features, and if you like, maybe can open up kind of these features and GitHub issue and we can try that. Then yeah, I'm obviously open to these improvements.
Okay, I think we have time for one more question, though there are two questions in Slido. So let's go with the most recent one, or the one that was asked first, which was explain the difference between environment modules and the one your app supports.
Second part was, and the what are apps?
And the one your app supports. The difference between the I'm assuming that standard environment modules and the ones your app supports.
So there's, if you don't know, so environment modules is a different project. It's environment modules is at the end, it's going to still provide you a module command. There are differences between environment modules in some of the newer versions that they have. They have different, let's say, options, like when you run like there's a lot of similarity between Lmod and module. I mean, environment module, like module load, module unload. But then there are key differences, like there's some different features, like I can't really remember exactly, but like for instance, module spider is only available in Lmod, but it's not available in environment modules. So yeah, they're two different tools.
Okay.
Lmodules focus on Lmod. So I guess my one question is, like, if anyone's interested in having something similar like this for environment modules, I mean, I'm not committing anything to it yet, but I mean, we could do something like that.
Okey-dokey. I think that's all the time that we have. Thank you so much again for your talk. There was one other question in Slido. If you want to take a look at that and maybe respond directly to the that question, if you'd like. Thank you. Okay, our next speaker is in person. Ren Stengel will be presenting on improving the accessibility of performance portable solid mechanics. Thank you.
Hi, everyone. I'm Ren. I'm a graduate student at CU Boulder. And so I'm going to be talking about the software that I work on that spends the majority of my time when I'm not skiing, and talking about how our little research group at CU has made some design decisions to try to improve the usability and accessibility of performance portable solid mechanics. Okay, so really fast outline. We're going to talk about what is Radel besides a Badger. It's the software that we work on. And then we're going to briefly cover what the performance portability looks like for this software package. And then we'll cover sort of usability and ways we've tried to improve that. Briefly going to go over some development standards, since this is a research lab. It's a little bit tricky sometimes to get graduate students to agree to keep development working well. And then we'll briefly touch on planned capabilities and some future work. So Radel is a library composed of solid mechanics solvers with the goal of trying to advance state-of-the-art constitutive modeling, solver algorithms, and performance portability. It is library-based with the goal of trying to enable separation of concerns, such as your solver configuration, as well as hardware architecture. And it goes about doing this by integrating the PETSC and libseed libraries, which we'll talk about in a second. And Radel defaults to using higher order finite element methods with matrix-free methods for improving accuracy and memory efficiency per degree of freedom of your mesh configuration. So right now, Radel is actually pretty new. It's only about 1.5 years old. And so the physics capabilities are very much a work in progress. But right now we support things like various boundary conditions like clamp, traction, slip boundary conditions,
We've recently added platen contact boundary conditions. We have a few different solvers like static, quasi-static, and dynamic. We're working on adding in material point methods. And then we have support for multiple material configurations on the same mesh. And then right now we're mostly working in the hyperelastic regime, so neo-Hookean, Mooney-Rivlin, some mixed elasticity, and working on plasticity like rate independent plasticity. So the first kind of like main dependency that Radel has is PETSI, which is a tool for writing, analyzing, optimizing properties, et cetera, of large scale numerical solutions. I'm sure a lot of you have dealt with PETSI and are probably wondering why it's included in an accessibility oriented talk. But PETSI provides scalable linear and non-linear solvers, a suite of preconditioners, domain management or like mesh management, matrix operators, time steppers, et cetera. It does offer a variety of GPU support options, including CUDA, HIP and ROCm, Cocos, OpenCL. It does have a lot of really flexible debugging options, as well as performance metric reporting that can be specified at runtime, and I'll give some examples about this later. It also has support for different mesh types. So if you like using Gmesh for an open source mesh generator, that is supported, or you can use Exodus, et cetera. And PETSI is kind of an interesting community because it is very focused on community. And so there's a lot of iteration, and the Radel team actually has had a lot of interaction with PETSI, including kind of like back implementing some issues that we found. libseed is the next big dependency, which is another library that is focused mostly on providing an algebraic interface for matrix-free operators, especially with higher order finite elements. And the nice thing about libseed is that once it's built, you have a very flexible kind of like runtime environment to rapidly swap between like hardware configurations. So at runtime, I can decide I want to run on the CPU, and then the next time I run it, I can decide to run on a GPU without having to rebuild anything. And so users of libseed only need to write their single source code and then can decide, I want the GPU backend this time. And so most users don't have to touch GPU code or any like hardware specific code at all. And so I've mentioned kind of these matrix free and higher order methods. And the main reason why we're interested in using this is because modern hardware is trending towards software that favors less memory usage and less movement of data. And so sort of a couple of years ago, but on the same trajectory, modern hardware is loosely doing about 10 flops per byte. I'm obviously not the expert on this, but the benefit to using matrix-free methods then is that they store and move less data at the cost of needing slightly more flops. And then we generally use a P multigrid preconditioner because it's a natural fit for higher order finite elements, especially on unstructured methods. It looks a little funny on here. Anyways, so one of the benefits of using this P multigrid approach is that we get to use P refinement instead of H refinement, which is sort of a way of how you are handling your mesh geometry and your solver geometry. And so the industry standard, which is highlighted by that arrow, is linear and low order. And we get for about 10 to the 4 global degrees of freedom, an error of about 10 to the -2, which is generally considered acceptable for most engineering tolerances. With H refinement, we actually see on that dotted green line that as we're wanting to decrease our relative error, we actually need more degrees of freedom and therefore more memory and space and compute power in order to get that lower error. But with P refinement, as we increase our geometry, we actually get to see that to an extent, we don't need nearly as many degrees of freedom in order to reach engineering level tolerances. And so this is actually like a really helpful and useful technique for being able to run large simulations without needing as many degrees of freedom, without the cost of having
excessive errors. And so these matrix-free methods have like a higher application of various operators on our like matrices. And so the solid line is our matrix-free setup that Radel uses. And so as we increase our solver order, we actually see an increase in efficiency up to the point of 3, 4, and 5 orders, fairly marginally close. But with the assembled matrices, which have many, many, many non-zeros per row, take up a lot of space, we see a decreasing efficiency as we increase the order. So matrix-free methods with higher order elements kind of go hand in hand, and they actually don't really work super well without the other. However, when we start to like run on these other machines, we kind of see a similar story of when we look at our efficiency in terms of millions of degrees of freedom per second per GPU. Some of these newer machines, such as Perlmutter and Crusher, actually perform and scale pretty well. And so the 8-node runs on Crusher. Our maximum kind of degrees of freedom is in right, the billions of degrees of freedom, and that fit comfortably on 8 nodes. Whereas with Summit and Lassen, we don't quite see the performance scaling as much. And so as we move in towards these larger, more GPU oriented and these new GPUs that are coming out, these matrix-free higher order methods are actually going to become pretty useful. But anyways, so for using Radel, there's a couple different options for how you would interact with it. And so the recommended way is to use a YAML file. And so here's just kind of a simple example of a very basic problem to solve, of where we're specifying our mesh parameters. This is just a unit box. And then we're using the neo-Hookean elasticity in a current configuration and specifying material parameters. And then we have our boundary conditions where we're specifying what sides to clamp, et cetera, and how much to move them. And then at the bottom is an example of some solver options that are all PETSI-based solver options. And then kind of in the bottom corner would be an example of how to run this on the command line. So you can either just pass in that YAML file directly, or you can obviously just spit all the command line options out directly on to the command line to run it. And so here's an example of what it looks like to be switching between backends. And so the first example is just using whatever the CPU has for you. And then the bottom one is using a CUDA-based GPU. And so you can specify that at runtime and swap as needed. I mentioned that PETSI can be a little bit of a headache to build. And so we do host a Docker image as well as a Singularity image to help kind of reduce that if you're not super concerned about having like very, very accurate performance ability on like high performance machines. And so one of the things that is nice is that, right, if you're kind of a brand new, maybe a student or something like that who wants to run some simple or hopefully eventually complex solid mechanics problems, all you need to do is pull a Docker file, right, and run the Docker file with whatever specified flags that you want. And it's very flexible, and you don't actually have to get into the weeds a lot with it. Another thing that we've considered is our approach to how we actually do the constitutive modeling. And so typically, right, like in Abacus, et cetera, the modeler would provide this free energy function, which is the psi-e function. And then in Abacus, for example, you have to provide this like delta psi, and then which gives you S for your residual evaluation, and then a delta S function. And additionally, in Abacus, you would have to provide that in, I think, all 3 directions and every direction you're applying traction to. And so it's actually very bulky to add a new model into Abacus, for example. And so additionally, right, like this delta S, like Jacobian evaluation can be really difficult to derive as you're model increases in complexity, as well as kind of in a stable formulation that's not going to give you like ruin your accuracy. And so we've looked at using an auto differentiation tool called Enzyme to help compute that Newton linearization, so dψ and ds. And so Enzyme is a package that actually integrates in with LLVM's optimization pipeline. And so it has inherent support for C, C++, Swift, Julia, TensorFlow, et cetera. And one of the benefits to using Enzyme is that it computes derivatives after code optimization. So it works a little bit better, right, than if you would be doing those derivatives before code optimization. It's obviously not perfect, but it does a pretty good job at maintaining that optimization. And so we've been working on integrating Enzyme as an option for model development into Radel. So that ideally, right, the modeler only has to provide that one free energy function, and then you don't have to deal with computing derivatives on your own. And so automatic differentiation simplifies that constitutive modeling. And so here's kind of an example of what it looks like in Radel to add in a model using Enzyme. And so you're providing this strain energy function, which would be like the equation I had earlier. And then you're passing it into Enzyme auto diff, which will compute that first derivative. And then eventually for your Jacobian, you're doing an auto diff again with Enzyme and then a forward diff. And so you don't actually have to write any of these derivatives out and like handle any of the math, which is really convenient. And so right now we have a couple different enzyme-based models implemented that match the non-enzyme ones. And so if you want to look at performance between the two of them, all you have to do is change the name of the model that you're passing into Radel. And so once things are fully implemented, it's really easy to switch and swap or to test things and compare. And one of the things that is kind of interesting about using Enzyme or automatic differentiation is that even though it is slightly more expensive than non-automatic differentiation methods, it is actually still quite a bit faster than using assembled matrices. And so even though you do take a little bit of a performance hit in terms of scalars slash like values stored, and actual time spent doing the nonlinear solve iterations, it is actually still very fast and a very feasible way to do constitutive modeling in practice and at scale. And so because it's built on PETSI, we do actually have a lot of flexible output options in addition to input options. And so you have access to all of the PETSI like log files, which gives you information on solver status, how much memory you've used, what your runtime was, how much time you spent with MPI calls, et cetera. And that is achieved just by adding a simple log view flag, or if you care about GPUs, it'd be a log view GPU time flag. We can also produce like visualization outputs like VTU or VTK files that are viewable in ParaView or obviously anything else that can view those. And we have a couple different options for what quantities you want to view, which include this diagnostics quantity or things by like looking at reaction forces, displacements, and strain energy more specifically. For some of these outputs, we do offer CSV output support. And so once you have your simulation run, it's really easy to get all of your results into a graph because, right, you can just load your CSV file into Pandas or Seaborn or Excel even, and have a graph made pretty fast for you with minimal effort on your end. We also do offer a checkpointing option where, so, right, if you are worried about running out of time on your run, or if you want to change your boundary condition configuration, you can just checkpoint your file, load, make the changes you want the next time you run and pick up where you left off. So as a research team, we have tried to put in effort into having good development practices. And so we rely pretty heavily on the GitLab CI. And so we have automatic testing for every single commit that every grad student pushes and every single merge request. We do automatic testing of every single branch on all of the different hardware backends that are supported by libseed and PETC, as well as several different build configurations to try to reduce how much we break things. And we also test for code coverage and formatting. And so we rely heavily on make tidy and make format to help make sure that things are incrementing smoothly. And so this is just an example of some different tests that we run. And so we have CPU tests, and we also have CPUs with 64-bit integers. We have our automatic differentiation tests, and etc. We do quite a few unit testing as well to make sure that no one has broken anything significantly. And so we generally try to assume that all untested code is broken, while tested code is just slightly less broken or broken in a predictable way. And so again, here's some examples of just showing how many we've passed versus skipped to make sure that our branches are going to work moving forward. We also try to rely heavily on the GitLab issue tracker. In my experience, it's hard for grad students to keep up and stay focused on using an issue tracker, but we do try to use it a lot and try to use tags to make sure that everyone is up to date and following what other people in the lab are doing. We do have a roadmap, which is loosely shown here, that integrates with all of our issues, and then ideally these issues integrate back into merge requests that we are working on. We also have put in quite a bit of effort, however, in my opinion, not quite enough effort on documentation. And so we maintain documentation on runtime and configuration flags, but we also put in quite a bit of effort into maintaining documentation about the continuum mechanics, modeling formulations, in particular on how to write these all of these equations in a numerically stable way. And so this is hopefully a helpful learning tool for either new students or other people using it. Like most people, we also have community and development guidelines as well in our documentation. So our planned physics capabilities include adding in some fluid dynamic models, as well as fluid structure interactions, hopefully a poromechanics solver, viscoelasticity, and plastic damage. For our workflow / interface additions, we're also hoping to add in Julia, Rust, and Python interfaces. We're considering adding a flops estimate for the auto differentiation models, but I don't think that actually works yet in Enzyme. And then adding better support for outer loop and UQ workflow support, especially since our run flags are so flexible. So yeah, to sum up, would like to thank my various lab members, as well as a lot of members on the PETC and libseed teams. And for the performance studies, we do have a paper on archive if anyone is interested in looking into that more, since I know I didn't really go into it very much. But yeah, that's all I currently have. So thanks.
Okay, there are no questions on Slido. Are there any questions from the audience?
So you mentioned that it's hard to convince some of your colleagues in the group to follow the conventions and do good practices, development practices, and things like that. Do you have any advice for convincing people? Because I don't think it's limited to academic research groups.
Yeah, well, I mean, my biggest challenge with PETC, for example, is that the documentation is hard to keep up because it is such an expansive software package. But mostly we've tried to just implement having other people in the group review merge requests. And so Jeremy is the main software engineer in the group. And so he reviews most of them, but he tries to encourage other people in the lab to also be reviewing merge requests. Just as a kind of a check to be like, oh, I missed the documentation here, et cetera. But I would really like us to like add in like more checklists, I guess, especially for documentation, because to my knowledge, GitLab doesn't really have a good way of checking that like your documentation is readable and useful versus like it builds. So that's something that I'm hoping to add in. But yeah, I don't know. Grad students especially are like, I just want to do the physics and make the things work and don't care as much about the other ones. But
Boss have any sway there?
Jed does push quite a bit for these good practices. One of the things we have been talking about recently is we need better practices with testing models before they're fully integrated in with like finite differencing and stuff like that. Because I think the tendency in solid mechanics especially is to like, oh, my solver converged, so therefore my math is good. And maybe it's good most of the time, but not necessarily at all times. And so those little things are things that we've been talking about adding in. But yeah, I mean, Jed is very busy, so he does as much as he can, but yeah.
Anyone else? Come on up. Yep. Got plenty of time.
There's time. I just have a comment. I don't really know how to phrase this, but I feel like going back to the trade-off of like high order methods, and we're always told that flops are free. And I always talk about this with my group, and we always go through and find something to test this on. Never come up with that, that conclusion. So anytime I go through and try to trade computing stuff for saving stuff in memory, it's never been faster for me, even on GPUs. And I can't think of a time, and I've done this over and over again. So like caching divides is a crucial thing that we still do all the time. And I guess I just want to mention, it is interesting to me if you're actually doing high order methods and it's proving fruitful for you to not save memory. I don't know if I need to do it on just like a more broad spectrum. Like if I took the whole application and just minimize the memory and maximize the compute, that maybe I would come out ahead. But it's like anytime I take a case that I can do in a day and try to compute things on the fly and not store them, I never win. So I don't know if anybody else has any more comments.
Yeah, my understanding in that case, from at least working on this paper here, is that higher order methods definitely in a lot of cases do take up a lot more memory and aren't as efficient. But the addition of using this like P multigrid approach is kind of what makes it actually tractable. And so this definitely isn't something that has gained a lot of traction yet. And so I'm very interested to see like where it ends up going. But yeah, I don't know, there's all these kind of like funky tuning flags that you can do. But yeah.
Oh. And we've got about 3 more minutes. So if there's any other questions, feel free.
Good talk. I mean, you mentioned obviously you're a grad student. There's lots of grad students in this group. And I remember when I was in grad school, it was sometimes hard to do software development because there's pressure pretty much just to publish, regardless of like whatever you're doing with code. So is your group doing anything to try to make sure that, you know, grad students are getting the credit for software development, even if it's not necessarily via like a bunch of papers or something of that nature, like are there DOIs or anything that?
Yeah. So I believe the Radel repository has a Zenodo entry for it, and I think a DOI. And then we have our authors list as well. That's been fully documented. There isn't like actually a super huge push in our lab to be publishing constantly, which has been kind of backwards for me. But yeah, so there's a lot more emphasis in software development and working on making things that, you know, are usable. And then like ideally papers are coming out of that. which I have found to be nice because there is less pressure to be constantly like publishing, and it takes a little bit of stress off. But software development is frustrating in its own, a different way. So yeah.
Thanks.
Okay, don't see anyone else in the audience asking questions. So thank you so much. We are going to a 30-minute break. So return back to this room at 3:10, and we'll have the final two talks for the afternoon. Thank you. All right. Let's see if we can go ahead and get started. We have two more talks for the afternoon, both of which will be virtual. So for those of you who are following online, don't forget to ask your questions in Slido. And I suppose that anyone who is in the room, of course, can come to the microphone if you'd like. So the next talk is, we have two speakers, or two authors, at least on this next talk. Sean Bruno and Dr. Patrick Carlson will be presenting on Podman versus Docker comparison via Rshiny project deployment. So I think they are ready to go. Looks like everyone's logged in and in Zoom. So I will hand it over to you. Thank you.
Thank you much. Thanks for everyone for hanging out this afternoon. Hope everyone got their required afternoon caffeine drink or whatever you need to make it through the last couple of presentations. Appreciate you guys hanging out. Professor Carlson and I wanted to present kind of some corner cases and some interesting results from our experiences at Sandia National Labs from deploying various bits and pieces of data science software inside of containers. We started with Docker and we found Podman. It was released to us via IBM Red Hat and as it came in from Red Hat's Linux distributions. And we found some interesting things and we thought we'd talk about it and see what if you guys have any questions about what we ran into, what experiences we had, and what we think of it. We'll give you some honest opinions. Generally this presentation is just going to kind of be, we're not going to get into the nuts and bolts of Docker, building containers, or how to use Podman. Realistically, we're not going to do that in 20 minutes. There's plenty of information on the internet about how to do that, great YouTube videos. What we're more interested in is these things are supposed to be 100% compatible. There's a great emphasis on the network, on the internet right now about OCI compatible images that you can load via. You can load the same image in Docker, you can load the same image in Podman. There's even, you folks are probably familiar with some various cluster compute style container systems that are supposed to be able to load the same images, which is great that there is a standard. That's the first thing. There is a standard for how an image is constructed, laid out, and how it's supposed to instantiate itself. The things that we were interested in, well, me primarily, were this concept of being able to instantiate a container without root permissions. I focus a little bit more on security and process separation for applications. And at Sandia National Labs, we try to emphasize that we try to provide scientists the capability to run their software in a safe and secure manner. And Podman looked like it was something that we should pursue. It does provide some interesting process isolation techniques via kind of this weird backwards mechanism of letting normal users run containers. For for this presentation, we're going to talk a little bit about some of our deployments with Docker using open source projects. We used Docker and Podman on Windows and on Linux to construct the paper that we'll be submitting for publication to this conference. So we consume our own dog food, and we try to make it as painless as possible for our users to eat that dog food as well. So let's talk a little bit about what we try to emphasize to our users. One is that, you know, if you're doing things with a container, if you're deploying your software via CI/CD practices, you're self-documenting. You're not having to reinvent the wheel. You're not having to think about something you did 2 years ago on some Snowflake system. You have it in a makefile. You have it in a GitLab runner. You've got some kind of build that exists in a system that can reproduce your system. So if you need to be audited, you need to justify a decision you made, it's there in code. You don't have to think about it. The machine just does it for you. In addition, we're running into situations where vendors do not release installers, zip files, any kind of standalone software. They hand you a Docker image and they say, here is our software, and you're supposed to do something. If you're lucky, you'll get a Docker image. A lot of vendors don't even do that. They simply say, go on to EC2 and start up the software via some SaaS mechanism, and that's it. They don't even provide you access to the underlying software. At this point, we have experience utilizing Docker, Docker on Windows, Docker on Linux, rootless Docker. I personally have experience with Podman and instantiating jails and containers on FreeBSD. Pretty much, if you're doing stuff on a server, even if you're doing something on a desktop, like Dr. Carlson and I did to do LaTeX and generate the paper for this presentation, we were able to kind of do that in a CI/CD way with a container to where we could share information back and forth, and we weren't leaking information through Evernote or some kind of other online service, or spending hours trying to set up LaTeX locally on different environments. It was good to use a reproducible scenario to generate the stuff that we needed. I'm gonna head off into Podman land now to talk about the rootless bits, which are very interesting. IBM, Red Hat, and the Podman project emphasize the fact that they really focus on being 100% compatible. All the commands that exist in Docker exist in Podman. You can theoretically, what this is showing you here is that the script, one of the scripts in Red Hat Linux called user bin Docker, is literally just invoking Podman with the same command line arguments. This is the way that they will accept bugs if you can do something in Docker and you can't do the thing in Podman. That's the first thing. They really emphasize the fact that Docker was first, and that this structure that Docker has established is the de facto standard. There's some arguments. IBM and Red Hat try to change the standard slightly, but the Docker project kind of drives what a container is, with few exceptions. So Podman does behave differently than Docker in certain very fundamental ways. The first thing that Podman does that Docker does, Docker has a daemon that runs as root, and you interact with that daemon to instantiate containers, change your network configuration, change your firewall rules for every container. It has a management daemon. Podman doesn't have any of that. You fire off a command, it does the thing and it exits. There is no standalone Podman daemon sitting around waiting for you to instantiate stuff. Most of the command line arguments, I tried to highlight here that the command line arguments syntactically are the same. There are some variations. Specifically, this is a Red Hat kind of driven project, an IBM driven project. They did sit down and think about the implications of SE Linux. So the little Control Z, if you stare at the slide, or maybe get the telescope out to look, there's a colon and a Z at the very end of the volume mount directive here. That's an indicator that they are doing something with SE Linux. They're remapping characteristics for you and doing something very interesting here that helps the interactions with security and hopefully allows you to get work done instead of just sitting there and, like everybody else in the world, going into your Linux machine and disabling SE Linux. We can't do that at Sandia National Labs. And we want to be able to provide people the same level of support without necessarily breaking security. So this is kind of a thing of, we're trying to work with the products that the vendors say are compatible. So again, this is a Podman invocation that allows you to run something that looks like a Docker command. And hopefully, it does the right thing. In our experience, it has. So this is the rootless stuff. The way in general, and I recommend doing a little bit deeper reading, the way that this is working and the way that Podman allows you to run a container as a non-root entity is that first, root establishes a remapping of your user ID. What does that mean? It means that we're going to reserve a chunk somewhere in the user ID space, a block of user IDs. And we're going to say, hey, we're going to remap those. We're going to say that all of the users that you create by starting up a container as you are actually going to run in this user ID space. What that effectively does, it means when root inside of a container is needed to run a program, it runs as you, but it runs as a remapped user ID. So it starts with your user ID, you're running every program, but the system is going to remap the user ID in such a way that it allows you and this program to coexist. So the program thinks it's running as root, it's inside of a container, but if you exit the container and examine the process, it's running as you. So there's no root involved. It doesn't have any, if it escapes the container somehow in a security, if something happens, something bad happens, and the application is able to escape the container, it doesn't have any more permissions than you, the non-root user, which is kind of the hope. So you can run these as headless users, you can run these as standalone users. You don't have to run them as yourselves. Obviously, on my machine, I have some amount of elevated permissions, but in this situation, you're allowed to run the entire container process as a non-root user because you're running it as yourself. But root has to set those things up first. This is how you can tell that there's a remapping involved, but also Podman doesn't directly, as a rootless user, you're not allowed to manage the firewall, you're not allowed to set up any networking rules. All of those things have to be set up beforehand by admins or people with elevated permissions. It's important to notice that difference. Docker will do a lot of this stuff for you, and it makes it a lot simpler. But if you're working in an environment where the security is important, your sysadmins and you will have to work together to compromise on what you're allowed to do and not do. This is where I'm going to hand off to Dr. Carlson to talk about Rshiny. Go ahead, Patrick.
Yeah, thanks, Sean. So so Sean kind of covered the sort of more technical underpinnings of comparing Docker and Podman. So kind of from more of a use case perspective. So Sean and I are both in the data sciences department, and so we provide infrastructure, software and different systems to support data scientists to kind of productionize workloads at Sandia. And so sort of given our experiences, from a containerization perspective, we were looking for solutions to help deploy Rshiny applications. So Rshiny is a library. It's under the R programming language. So R and Python are really kind of the top two languages for data scientists to use. And Rshiny is really nice because it allows folks to develop kind of dashboards, visualizations, kind of custom reports and things. Think drop-down filters and checkboxes and ability to download data and things like that, and have graphs similar to what you'd see with other sort of dashboard visualization tools like Power BI and Tableau, things like that. But it gives you a little bit more, or I should say a lot more, ability to do customization. So it's a pretty popular tool for that. And so we looked around and ultimately found Rshiny server, or Rshiny proxy server, which is an open source project. And essentially it's able to run as a container itself. And you're able to essentially give it containerized Rshiny applications. And it's able to essentially host those up for access in a web browser and provide all the sort of niceties of having LDAP authentication for access controls. And you can pass in environment settings and things like that. So next slide. So here's kind of a quick overview of, for the Rshiny proxy server, how we did some of the setup in the Docker file. Pretty straightforward, but basically we're adding some certs there to the trust store. So Sandia essentially has its own internal sort of root certificate so that you're able to make connections to external resources. Think I want to connect to Google, and that way Sandia is able to inspect and decrypt that traffic and look at it if it so desired. So that's kind of getting the cert set up. We go through and install just some packages for debugging purposes. And then an important part, so there's a YAML file, this application YAML file that gets added to the container. This is where you're going to define all your applications and things that you want to run. So basically you go in and define these are the particular applications, and these are the LDAP groups that I want to have access to that application and things like that. And then lastly, down at the bottom there, the environment files also get loaded in. So these are sort of, again, per app settings. So think database connection strings, passwords, secrets, anything that is sort of customizable that you want to parameterize your application with. Next slide. For both the Rshiny proxy server as well as the Rshiny applications, all this is kind of set up through a CI/CD pipeline, and we use GitLab and GitLab runners to deploy all this. So if you're not familiar, so GitLab is kind of an on-prem hosted version of, it's essentially very similar to GitHub. So I'm sure everybody's familiar with that, right? But to be able to do version control and have kick off CI/CD pipelines and track issues and things like that. So we have GitLab internally at Sandia. And so basically for the Rshiny proxy server, we can go in and make changes to the application YAML file, let's say, and adding new applications that people want to host, or let's say if or when the Rshiny proxy server, the base image gets updated, right? We can go in and make changes to that. And all of that kicks off a deployment through GitLab runners. So we have a build server that builds the image and then pushes that back to the container or image registry in GitLab. And then there's a separate stage that goes off onto the Rshiny proxy server. So this is just a VM that's set up, and then pulls the image and redeploys the container. And it's essentially very similar for the Rshiny applications as well. So for people that are doing development, they basically just go in and make changes, and that's sort of all, again, hooked up from a deployment perspective to build the image, and then essentially make sure and push that image and make sure it's available on the proxy server for running. Next slide. So for data scientists, kind of, yeah, like I talked about, we have a template that they're able to use and fork to from GitLab to have kind of an example of a containerized Shiny application. So it's just a simple example. So they can fork that, make changes, and they can do their own local development using RStudio Connect. So and RStudio, I guess as a company, they've rebranded now to Posit. But essentially they're the main kind of commercial entity behind R, and you know, they do a lot of development and effort towards Shiny and so on. So you know, data scientists can jump in, you know, do their development and testing there, and sort of prep that container image on their local machine. They can then push those changes to GitLab, which then kicks off a build, and then ultimately stores the image on the Shiny proxy server. And then on our side, from a sort of sysadmin perspective, we basically just need to add their application to this YAML file, and then any sort of environment variables that need to get set in terms of credentials and things, we basically just generally do that once. And then obviously any kind of LDAP groups that they want to sort of restrict access to. And then for the users, as long as you're in that particular LDAP group, you can log in through the web UI, and then the Shiny application executes. So the kind of neat thing in how it works for the Shiny proxy server is you end up doing a bind mount in Docker back to the Docker daemon. And so that enables the Shiny proxy server to essentially have access to all the underlying images and things within the local machine. And so that's how it's able to spin up a Shiny application as its own container, basically. Next slide. So from a value perspective, right, for data scientists and users and so on, I think there's a number that are really important. So, you know, the first is just to be able to quickly deploy code and changes and have Shiny applications in an automated pipeline. And, you know, it's not a case of, oh, well, I have to, you know, SCP or FTP files someplace, or, you know, anytime I make a change, that can be, you know, kind of an annoyance, right? That you're really trying to leverage those good sort of software engineering practices from a CI/CD kind of DevOps standpoint. The other is we've had a lot of success with data scientists exposing analytics and models, really ranging from, you know, your basic, you know, descriptive reporting through to predictive and prescriptive models, and sort of having Shiny be the front end for them to consume that work and really share it with others. So I think that's been really helpful, and we have a number of deployments of models like you know, looking for security infractions, things like that. So kind of, again, more predictive models that we've deployed to Shiny, and then folks are able to easily consume those. The third one, so, you know, reproducibility, right, is another really important thing that I think often is overlooked from a data science perspective, that, you know, instead of having this sort of shifting sand, right, where you have underlying libraries at the OS level that are changing, and you're, you know, sort of constantly potentially run into issues of changes there, you can really work to, you know, because everything is containerized, try to lock that down and make sure that you're running particular versions of things that you need. The last one, you know, from a security perspective, and this sort of goes against the third point there, but you know, it is nice also to be able to automatically find and update, you know, containers and things. So a number of our services have and deployments, not just the Shiny proxy server, but others that we've containerized. We have scheduled rebuilds every week or so. And so, you know, that essentially goes through and forces a rebuild of the entire container. And so, you know, if you have, you know, underlying updates from your base image, let's say, you know, you're running from Ubuntu, and Ubuntu revs some particular package, you want to be able to, for a security issue, you want to be able to, take advantage of that. So I think it's kind of a mix of making sure that you're, well, multiple things, right? Making sure that you have a small attack surface, right, that people could exploit, but also trying to make sure that you're rebuilding on a reasonable cadence, and then trying to make sure that you're from a Rshiny perspective that you're deploying libraries that are of a particular version if you need that. Next slide. And yeah, I guess Sean, do you want to finish us off?
Yeah, and so this is kind of the wrap-up slide. Things that we ran into, corner cases where compatibility wasn't so compatible. So Podman by default treats networking differently than Docker does. Docker assumes full control of the networking on your machine and will make changes and treats the devices differently than Podman does. A good example is that interface names inside your container, if you show interfaces, ifconfig, whichever tool you enjoy using, you'll see a different device name in a Podman container versus a Docker container. This came up and frustrated me for a good amount of time, because certain license managers like to use the MAC address of a machine to generate a valid license key. And in a Podman container, just didn't have a valid network interface name. It was like TAP0 instead of ETH0. Was very frustrating. Still waiting for the vendor to fix that. They probably never will. Docker definitely needs root. Podman will run, if you treat Podman like Docker and run it as root, you'll get most of the same functionality out of Docker. I haven't run into a situation where giving Podman full root access did anything differently than Docker does. There still are some compatibility issues that are very subtle. And if you ask the Podman folks, they call them bugs. And if you ask the Docker people about them, they call them features. So they are playing nice together, but they're still, be prepared to spend some time debugging shell scripts and your pipelines. Docker Compose is a very powerful tool. There is something out there called Podman Compose. It's not as functional as Docker Compose and not as well supported. Docker Compose will use the Docker compatibility shims that Podman provides, and it will work most of the time. I would recommend caution if you have a pipeline that uses Docker Compose. Probably just stick to Docker unless your security folks come into your office and start yelling at you. Finally, SE Linux works way better with Podman than it does with Docker. That's something that should be obvious for folks who have had to use Red Hat / IBM Linux over the last few decades rather. SE Linux, comes from, is actively being supported at Red Hat, comes from our friends at the NSA originally. Docker, a lot of Docker how-tos just say to turn SE Linux off. It's frustrating, but true, and it does resolve some problems. Podman has feature flags and compatibility things for bind mounts to remap and reset SE Linux properties, which you might find useful. And that is it. This is the part where we ask for questions. If you need to get a hold of us, Dr. Carlson and I work at Sandia. You can find us and track us down at your leisure. Thank you.
All right, great. Thank you so much. Let's give our presenters. Okay, so we've got about 2 minutes for any questions. So we've got some here in the room. So we'll go ahead and get started with those questions. Go ahead.
Hi, thanks for the presentation. I have a couple of questions.
related to your experience with these two programs. First, have you experienced a practical size limit on the usability of containers if you're doing things like CI or continuous rebuilds? Because once certain compiler stacks can get rather large, they get up to like several gigabytes, and then you start to run into these kinds of timeout issues and things like that. And also, there's now a rootless Docker. So how does that fit into the equation?
I'll address the second one first. Rootless Docker is great, and I'm glad that there's competition in this space, because the rootless stuff for Podman really put it into a very interesting space where it was kind of in competition with Docker, where it was like, oh, it's got this feature that Docker just doesn't have. But now that Docker has that feature, it kind of like means that we don't necessarily have to make a choice. Depending upon our environment, we can kind of either we can standardize on Docker, we can standardize on Podman. For space constraints, a lot of the machines that Dr. Carlson and I interact with, we have control over the size of the bind mounts that we pass into the containers. That's really hasn't been an issue for data. And then when we build the containers, a lot of the times we're building them from scratch. We're installing and sizing them and shoving them into pretty large image repositories that are self-hosted. Is that kind of where your questions were going, or did you have something more specific about size constraints?
Well, I'm wondering if I'm using like an LLVM compiler with a bunch of GPU add-ons and GPU libraries, and all of that stuff comes bundled, and it's 4 gigabytes. It seems awfully slow when I try and run it, so I don't know how to get around this space.
So performance, you're having like instantiation and performance constraints because of the way that like you get this giant pile of a container, right?
Yeah.
And it's not like super nimble to like instantiate the container when it like has to fire up all this stuff. A lot of the stuff that you have to do for performance with containers is doing a lot of memory-backed file systems. I recommend that there's a lot of folks on the internet that are looking at how you use TempFS and MDFS and other memory-backed file system techniques to accelerate the runtime, but the instantiation is going to be yanking that stuff off of disk or off the network, and it really doesn't speed up. So like when you're pulling in a container that has a full LLVM tool chain, it's just not going to be fast.
Ideas, though. Thanks.
All right.
Thank you so much. I think we're out of time. Appreciate that. There was one comment in the Slido, so if the authors would take a minute to take a look at that later, that'd be awesome. As well as everyone else. So we are on our final talk for the day. Let's get on the right screen here. So our next speaker is Dr. Constanze Roedig from Vienna University of Technology. The title of her talk is Cloud Native Open Science Labs for HPC, Easing the Road to Fair Collaboration and Open Source. So I will go ahead and give the floor to you.
Good evening here from Amsterdam. It is almost midnight, and thank you so much for bearing with me, and thank you so much for having me on today. Yes, it is my pleasure to represent a couple of Austrian universities here in this collaboration where we, the Austrian side represents some computer scientists, platform engineers, and cloud security specialists that we teamed up with people from the HPC space, in fact, Johns Hopkins APL, and the people from NCAR to give us a first real-life test or stress test of these, what we call open science labs for HPC. And the whole idea here is to make the entrance barrier for high-performance computing easier and to enable interactive collaboration. And just in case I forget to say it later, This is not to run HPC applications in containers. This is to use containerization, cloud native tooling, and a lot of what we've just previously heard, also a lot of hiding security controls using SE Linux in the background, hiding all of this away, using the technology and leveraging it such that a scientist can actually focus on their science, but also do it interactively, and portable. Now, that would be the introduction. I, of course, am not doing this alone. I am very happy to represent here a lot of co-authors from various universities. And of course, I'm very grateful for our funding agencies. Also, if I'm using in the name Pokeball, I do respect the original copyright. Yeah, so the agenda is lots of slides here, most of them just for reading later, and I'll skip over some of them. The idea here is we want to enable usability, ease of use in this very niche field, which is HPC. And I myself, I'm a physicist. I used to do lots of HPC before I went into cloud and cloud security. But this is all about making it a little bit less tedious, lifting a bit of the toil away from the way that we can do open science, and also maybe the incentivization of doing fair requirements and open science requirements can be quite annoying to some maintainers, and maybe there's something we can do in terms of leveraging technology for the people. So the two perspectives that I would like to talk about is the one is the end user, the researcher, meaning that could be a student, that could be a peer reviewer when you submit a paper, or it could be a senior scientist. And the admin perspective, that be the person behind the scenes, that might be your security engineer, it might be your platform engineer, your HPC admin, or even the owner of the institute who needs to make cost or investment decisions on this. So I'll just give you some gists of the overview of the sample size is currently 1. This is our first real test with real people. And what are these use cases that we had hypothesized when I was last year around this time over in Baltimore, and we talked about how cool would it be if we could have paper companions for HPC code, where we always have to choose a particular slicing and dicing of these really large data sets. But it would be really cool if we could give that to a reader and they would turn around the 3D images, have maybe some GPU support in the back end. And, so we could give them, or maybe zooming in, we could give them control over some paper plots in a semi-live session. A bit more, but similar for a peer reviewer. We could even give them access to shock tubes, one-dimensional convergence tests and the like. And then there are the next two use cases that have to do with learning HPC code and making it easier to get started. If you've ever tried to compile an older HPC code base that has legacy parts in there, you may know that it's not always super straightforward to get something to run. When I took this Fortran plus Python code base here, and I hadn't compiled Fortran for like 10 years, it did take me quite a bit of time to get back into the game. And so what we try to do here is have an interactive browser session, couple minutes for the container to pull. Yes, those container images can be up to 28 gigabytes, but we still get them to boot within 10 minutes or so, and then they have relatively good performance because we have beefy backends. But yeah, so still it's a lot better to wait 10 minutes than to compile the whole thing and then figure out while your particular package is not linking or something. And then the other two is doing outreach or simply open sourcing your code and having also a executable to go with it. Again, we're not focusing on performance optimization, we're focusing on portability here. Right, so that's what we had sort of in mind. Can we do this? And just to give you the overview of what we cover here, for the scientists we use, that we always think about the top flow. We have in Git somewhere an application, could be Fortran, could be C, could be whatever. We build artifacts such as Docker containers or containers of any form, OCI compliant, in fact, and then we run them in a browser and have it in a way that we can interactively access it. So exposed to the internet, of course. but the infrastructure on which that thingy has to run is also completely controlled by GitOps processes and goes down almost to the data center. So the data center, of course, is in the control of the country or the institute. On top of that, we have several cloud providers. We've currently tried out some private ones and also some public ones. And the important part is that there we have a container orchestrator, and this is the one where we decouple the choices that are local to an institute and the ones that we want to make translatable. Our Kubernetes in this case, this is this steering wheel, it symbolizes Kubernetes, which is the most standard container orchestrator out there, is one that is portable. So we sacrifice some cost for portability across several cloud providers here. And we also build a lot of security into that layer, into that platform layer, so that we can hide it away from the user up top. And doing this all as a community. So that's the idea anyway. We have to prove if that works. So the 2 points here is how can I share it? What do I have to do in the backend? That's one big question. And the other big question is, how do I have to wrap my application in order for this to run securely in the backend, because we have to expose this to the internet. So this slide could be a very long conversation, is like, why is it hard to publish and teach HPC? The two things that I would like to highlight is that I think it's important to make it a bit more enticing, more attractive, and just easier to get started with it, also to attract students into the field. And the one that I'm personally more involved in is like helping to bring the burden down for the maintainers when they're doing stuff that they're not really, their careers are just not incentivized for. And with that being said, what is the setup that we've been trying out here? So starting in Maryland, we have a Bitbucket repo with the Fortran and Python code in it. Then on Cheyenne, which belongs to UCAR, we're running a standard HPC calculation that puts out probably terabytes of results data in H5 format. Then we built the same application, completely the same steps with the same makefile into a OCI compliant container. That registry is hosted on a public cloud in West Europe somewhere. Then we have a home directory on a Ceph cluster in a private cloud somewhere. And in another private cloud, we're hosting a Kubernetes with a special Jupyter on top. Now, I just said Jupyter. I'm pretty sure that most of you have come into contact with it at some point. We use it here for having a way to have a web shell exposed to a user in a browser, where we give that user the illusion of having almost a full operating system and full freedom. But in the backend, we're actually, and this is what that thing looks like, in the backend, we actually have quite a few controls on it. So it is a container, and we try to make sure that people cannot get out of this container. So what is specific here is you log into your browser, you see a drop down, you find your image that you've previously built. You have drop downs with like a CPU or GPU scheduling, how much memory you can have. And we've also solved the single sign-on for you. And then another thing that is relatively cool about Jupyter is that it's very extensible. Here in the background is something that a couple of students built, which is an auto-grading application, just as an example of that. If you need a feature, you just add it into Jupyter if you really want it. So now, what exactly is an Open Science Lab? It is basically a combination, depending on your perspective, either the software as a service, so the Jupyter part where you put your own HPC application into, or it is including the platform part, that Kubernetes part in the middle. Zooming into that previous image a little bit more, that's what it would actually look like. And all of this, so the layers, red, blue, and orange are actually open sourced by us now in the first version. So we have Terraform and Ansible, almost 100% automation to instantiate the entire cloud setup. Then on the cloud, which is the red layer, then on the cloud, we can instantiate various tenants of Kubernetes. And in that Kubernetes, which is the container orchestrator, we can leave users the freedom to bring in their own applications and host them in Jupyter. And we hope to have done this in a way that is highly federated, so we can work across the globe. What we call a profile for open science is essentially a couple of value files that are very specific to make this HPC code base work by choosing, for example, SELinux profiles to have mount points for Globus in there. Globus is a way to, which we're going to see in a second, for sharing data. We have, for example, ParaView rendering enabled, that is 3D rendering. And what else? Oh yeah, and we're working on an intrusion detection system based on eBPF that we also have to build something into that, or compile something into the kernel specifically. And that's a profile that gets instantiated if you choose, okay, I want this version with this Pokeball profile, and Pokeball basically means putting a monster, which is this ancient and huge HPC code base, into a container. What are you doing? You're building a Pokeball. Sorry for that one. So what do you need to do to prepare? And that's always the same. You need to build a container, and you need to build it properly. I will not spend time on this now, but it takes a while to really build these huge containers with all those dependencies properly. And the current ones, the full ones, are actually sort of 25, 28 gigabyte large. Now, so how does it look in practice? So this is left, right, a before, after image here. So on the top, we see a researcher in Baltimore, for example, committing a change to their code. What triggers then remotely here in Vienna is a build agent builds the container, pushes it to the registry. So far, so clear. But what's also there is that we have a second webhook implemented that calls a template and injects into a specific Kubernetes instance that we've designated for this project with APL, a slight change in what is called a custom resource definition, such that now this new image is available to a specific group in the identity provider, and now appears in the drop-down available again with a certain quota to the end user. And I'm going to walk you through how that actually looks in practice. So the first step is here in Bitbucket, somebody pushes a push on a specific branch that has a trigger enabled. So the build is triggered. This build is actually happening in a different repository, in a different build environment, which we have here on our side of the ocean. And once the image is built and pushed, then we have the third step, which is deploy to a cluster. And what happens is that the kube control apply is happening, and we have a profile being configured. And now this newly built image is ready for consumption. And people can log into Jupyter just as they did before. And what they'll find is now, whatever, maybe we've made a change to this notebook. This is a Jupyter notebook. This is Python for an interactive tutorial here appears, and the people can now work together here in the Jupyter session. I said before that on the left side, we see here some group shares, and those group shares are for this research group to work together on these files. There's not much going on other than we also use these sub-UIDs that we've just heard about. So we have to do some mapping in the backend that the access rights are properly set, because you come in with from a, let's say, a modern OpenID Connect provider, and to get that mapped into the UIDs on Linux takes a bit of magic to happen, and we're still working to make the security tighter here. But essentially, you come in and you end up with exactly the correct, completely rootless access to your files and to your data with the right quota. Now, data gravity is a real problem. Just quickly, so we currently load data over the internet with Globus endpoints, and we found a way to instantiate within Jupyter, again, without capabilities, without privileges, these Globus sessions, where we can then bidirectionally, if you look in the top right, inside that container, we can open a bidirectional stream from the Globus endpoint to us. And so essentially between our Ceph cluster and somewhere there in NCAR, we can drag and drop the data in between. And this is very, very nice for security, very, very nice for usability at the moment. For the pure data transfer, I mean, that's just what it is, and that remains hard. So we're not mounting large terabyte files over the internet. That's probably not a particularly great idea. I'm going to skip this particular slide just to make a small annotation here. So we also built like this 3D kernel into the Jupyter that has had a lot of applaud from the physicists. And the other part that we've had is we had an extension enabled to view these H5 files interactively, which has also been found to be very useful. Now, the question really was, can we work together as like new joiners to, in the browser, simply type make, or in this case, cmake, and the whole thing is just going to compile and I don't need to install anything? And the answer is yes. So what you see here is we've prepared the environment, the container, in such a way that you can just write cmake with a particular flag. It will build a link and it build the Fortran code in this case with exactly the right Intel compiler and the H5 wrappers around it. And then depending on how much CPU you gave that code, you can also run it. So, and this is really where the performance then comes in. We typically run it here with like, I think 20-ish threads or so. So this is not HPC, but it is, at least you can run, get a feel, get a gist for how the code is working. And again, within a couple of minutes, you can start playing with the code. We just need to prepare good examples so that you can do something that is physical and it's representative. You can do something, non-trivial, while not using a full HPC CPU available. Right, so that was the, I still have not that much time left. I'll just jump over to the admin perspective real quick, what we had to do in order to make this work. So again, for the end user, it looks pretty much like they have a VM, they just don't have a root on it, but they can install quite a few things in user space. So for us, Jupyter is a web runtime with strong access controls. We've modified it to have more interaction on the RBAC and the role-based access control side. We've written a Kubernetes operator and open sourced it to do this dynamic injection of quota network access controls, which we're actively further developing, and it's very nifty. And we also had already a pen test on our setup, which we use here, both defense in depth and time-based security, so that we can hopefully by logic and not by paying vendors for doing security for us, make it as cheap as we can to have a good idea of the security, or at least even if we have a compromise. So we try to make it as difficult as possible to have a compromise in the first place by using pretty much all best practices that are affordable, but we also are aware that it's much better to have everything rotatable, and we're making a lot of use of the automation to say that we can dynamically rotate out these environments on maybe a weekly schedule, or any schedule actually that we want to have, that all the keys, all the network, all the access gets removed. So any persistence that might have occurred in a local data center could thus be wiped. And yeah, so what, I'm going to skip this one. So what is specific about this Kubernetes setup is that we really spent several months, even half a year, simply on hardening it out to a nice compromise between usability and hiding it away from the end user. And always keeping in mind that we have to be very cost and maintenance aware with all these choices that we make. For example, we use very strong network segmentation on a macro level, on the cloud provider level here. We completely separate the runtime from the state. We proxy in the mount points for the long-time storage. We try to have this mapping between the sub-UIDs, which we're somewhat mimicking because we're not using Podman, but between the sub-UIDs and OpenID Connect, which is also not yet perfect, but we're also working with some kernel developers. If maybe with Mount D we can do something better there. Ongoing research. And then we segmented more on the micro level as well in the network stack, and make a lot of choices here that are not necessarily standard when it comes to certificate handling, DNS, and like proxies that intercept things, so that it doesn't accidentally happen, because it happened, that users will expose, for example, databases or even Jupyter Hub endpoints to the internet at large, which is absolutely not what you want to have, as if you are sort of the platform owner. And I promised as the last part to give a bit of a hosting provider choices. And here, what we looked at is always, again, the audience for each use case. And we evaluated would it work, and where would we host it, and is it actually feasible? And we would conclude at this point that the onboarding and summer school use cases, so that people can quickly work together interactively on the same plots with, you know, maybe 1 terabyte to 5 terabyte of data, that works really well. The paper companion and peer review is actually harder than we thought. It's mostly because of identity. It's mostly because of the federated identity. And the open sourcing with the artifact to build that locally, if you can accept that you will not get performance more than your laptop can do, also works actually quite well. And yeah, I'm out of time here. And now I didn't put this in the slides, but so what is a cost point for this? So currently, with a lot of grains of salt here attached, because obviously lots of things can change. So we're currently calculating around €1,000 for one lab. If you have a decent size, let's say like 50 labs running, then yeah, we currently estimate around $1,000 per each one. Going forward, we're of course looking to work with many more research groups to make this better. The initial results are promising, and I think one thing can be said, we were actually quite surprised on how easy some things worked. And the whole federated access is the most crucial thing on the end user side, I would say, and to have good examples for the automation, for those YAML files, the CI/CD files that in our case, the physicists were not necessarily used to. For the admin perspective, I would say the thing to solve is staffing and skill sets. So we're working a lot on the training part. The security impact, I think, can be manageable if you really take it serious from day one. And the thing that drives cost the most is being portable. And yeah, we do have this stuff open sourced. If you're at all interested, and in any other case, I really thank you on behalf of all of us for listening and for your time and for hanging on there, like at this last talk, which contained a lot of info. Thank you so much.
Okay, thank you. All right, thanks for the talk. Any questions in the audience? Anyone? Yeah, it's not as late here as it is there, so thank you.
Yeah, I echo. Thanks for sticking on. You had mentioned, kind of generally, the balance you had to strike between hardening the infrastructure and having the capability for the end users. Were there any situations that you ran into when you were working with the end users where they wanted to do something, but it just couldn't be done in a secure way? Or is that not really been an issue?
Not really that it couldn't be done. It's more that they would assume, oh, well, I want sudo, and I know how to do it as root. And it would just take a lot more effort to do it without privileges, or you would have to pre-build it into the containers, or even install it on the Kubernetes nodes to make it possible. I was actually surprised how well SC Linux worked, because usually it interferes. It did not much. I would say that the whole mounting part that's the crucial one that is still hurting us with the privileges. Everything else seems to work okay.
Thanks.
Hey, there's a question on Slido. Patrick Carlson asks, would you comment on your experiences with Globus? Has that been easy for researchers to use for collaboration and data sharing?
So I had not previously known of it, and I've been amazed how easy it is. I would not want to comment at this point in time on how easy it is for me, for us as the engineers to use, because we don't have accounts ourselves. We always use the NCAR endpoints that are given to us. So I unfortunately have to defer that question to when I have more experience with it. I apologize.
Okay, any final questions? There are no more questions on Slido, so. Anyone going once? Twice? All right, that's it. It's a wrap. Thanks, everyone. Let's give another round of applause for our speakers today. And we appreciate everyone's participation. Thank you.